das mit den kaputten Gabeln ist immer ja
hello, hello. Wait, I never know how far to hold these, so it's kind of weird. Anyway, welcome everybody to the Julia for HPC mini symposium. We're kicking things off rather punctually today. And so, as our first speakers, we have Billy and Sam. So, Billy is from UIUC and Sam is from the Swiss National Supercomputing Center. And I'll let them talk about what they're going to talk about. Hey, which one's first? All right. Okay.
Yeah, so welcome to our talk uh, called From Stencils to XLA, a React and Backend for Power Stencil. And he already introduced us. So this will be a talk, it's a collaboration together with Billy. And so he will give a little bit of insights from the reaction side later on. Right, so let's dive right in. Some GPU generations ago, uh, it was very hard to get close to uh, peak performance or close to a theoretical upper bound for performance, um, even for a simple solver like a 3D heat diffusion. So here you can see a plot showing results we got with a P100, V100 GPU. So these are old results. Now, if you would run it again, it would get a little bit different. So we focus here in the center. So you see with explicit CUDA, we got only like 50 to 60% of the possible peak performance. And then with parallel stencil, thanks to automatic optimizations, we could push it up very close to the theoretical upper bound. And so we could see that we really needed automatic optimization to get close to the best. So they were really impactful. And so what I was showing there in this plot, what was the benchmark used was this here, very simple. So this was an explicit, straightforward way to program this 3D heat diffusion. It's really just explicit finite differences. And you can see the index computation in yellow on the top is the only thing that changes when we change between CUDA or kernel abstractions or the explicit version of parallel stencil. And then for parallel stencil, we had this memopt equal true flag to activate the automatic optimization. Now, we got a new situation. On newer GPUs like the H100 we have at CSCS, suddenly, if you do the same, with CUDA, you get almost to the peak performance. You don't have to do any particular optimizations. With parallel stencil, we can get a tiny bit better than still, but I mean, we're already at the top almost of what we can get. So question comes up, is automatic optimization not needed anymore? Of course, now to think about that, we need to think about real world applications, bigger ones. And so in this talk, we want to investigate this with a 3D stock solver as a proxy, where we have multiple coupled equations, staggered grid, and so on. And then we want to see afterwards how to integrate React and Best in parallel stencil in order to optimize real world applications. All right, so the agenda of the talk is very simple. We look at the effective memory throughput of the 3D Stokes solver. Then Billy will talk a little bit about the reactant side. And then we evaluate different ways to integrate parallel stencil, reactant into parallel stencil. And then results and conclusions. Okay, so the effective memory throughput of the 3D Stokes solver. So first we look at the solver itself. So we say, okay, let's apply this high performing approach we used for the 3D diffusion. We used, again, explicit straightforward kernels, finite differences, and hope for the best, right? I think it will be as good, hopefully, right? Uh, so here it looks how it looks concretely. We'll have then typically 3 kernels where we compute divergence of V and the pressure first. Then we synchronize, right? We compute stresses, we synchronize, we compute velocity, we synchronize. So we always need to synchronize in order to avoid that same fields are written and read at the same time such, and we could get race conditions. So now this is the first kernel. Very simple, as I said, same style as before of the performance, high performance diffusion version. So the same style. The only thing that changes between Ka and CUDA, etc., is just the indexes on the top. Again, explicit finite differences, very simple. Then I show you another way of doing it, just because later it will be important. So with ParaStencil, we can write this with some high-level macros. And so we get just, for each equation, we get 1 line. So you see 2 equations, 2 lines here. For the second kernel, 6 equations, 6 lines, right? Then 3 equations, 3 lines for the third kernel. Okay, so let's look at the effective memory throughput metric for those who are not yet familiar with that. This is pretty straightforward to compute. We have the effective memory access, AF, which we define as 2 times the unknown plus the known. The unknown is the memory footprint of the unknown fields that depend on their own history. And that's very important that they depend on the history. So they are fields that are updated every iteration. Then the D known is the known fields which do not change across iterations. And then, so when we have defined this, then it's very simple to get a throughput from that. We just divide by the execution time, TIT, and that's it. Then the upper bound is also very simple. It's T peak memory throughput, as measured by, for example, stream for CPU or something analog on GPU. Here's some assumptions. I'll leave them out. The key is to really understand what it's about, right? So every iteration we need to read and write the unknown. And that's why we have this factor 2 there, because we have 2 accesses. We only read the known, so there is only factor 1. All right, so how does it look in practice? For here a 2D diffusion example. So we have the unknown variable T, the temperature. So we do 2 times 1, because you have only 1 unknown. And we have the heat capacity here, Ci, which is the unknown field, so +1. That's it. And the rest of it is always the same, basically. And so very important here, we don't count the fluxes, we don't count the heat fluxes, because we can compute them on chip. They do not depend on their own history. All right. So now I think, okay, in the throughput, in the 3D stock solver, now what do? We have there 3 kernels, right? So do we compute now this for each kernel and then take a weighted sum of this or something like that when we want to assess the application performance? Or instead, well, we just try to apply it, to apply what I showed you before. But we think maybe, okay, we need to include still the stress components, which are 6. and we need to include the velocity. Sorry, the divergence of the velocity, and end up in the end with 11 accesses. But well, you guess already. No, that's exactly what we must not do. So we, instead of this factor 11, we get a factor 4, right? Um, uh, so one might think, well, but then is there an issue with this definition of the effective memory throughput? Because we introduce these three kernels and all these fields, the stress components and the divergence, in order to avoid race conditions. But actually, if you really think about it, we can fuse the three kernels into one. And you will see later more about that. Then I will leave out this part. It's just showing that with these other two metrics, we would overestimate the application performance. And we can also see, if we look in detail, that if we use this wrong constraint, that we can not fuse the kernel, we actually limit ourselves, we reduce the maximum achievable performance. I will leave out the details here for time's sake. Just here, something very easy to grasp. So here I measured for a particular run. So we got the same runtime 3 times, right? Or it's actually the same, it's only one runtime. And so we computed here the effective memory throughput in these 3 ways I showed you before. And we get an overestimation of up to 3 times. So the TF in blue is the right one. Okay, so this was just to make you sensitive a bit to how important it is to measure things the way we want. And so then I measured actually the throughput of the 3D Stokes solver with these 3 kernels. And you can see all explicit codes here, all this straightforward code, are 7 to 4 times below T-peak. You see in the vertical, again, the effective memory throughput, and on the horizontal are different packages that we use to implement that. The Tulio, Jack, kernel abstractness, CUDA, and so on. And part of the stencil in different ways with optimization. And so first we can see, well, yeah, with a straightforward implementation, we don't get anything good. And our and optimizations don't help a lot either. And we can see, I mean, if you look at the distance between the peak throughput and where we are, we can improve up to 4 times. Now this will be challenging because if we fuse everything into one kernel, there will be much more computations in the same kernel and a lot of pressure on the on-chip memory. So optimizations are very important. But there is a title missing. Okay. Yeah.
Cool. So before we go in and explain a little bit more about that gap, I personally find it very helpful to understand how sort of like the fundamental compilation of GPU code works. Now, here I have a little bit of a sort of like C++ CUDA code snippet. I know we're at JuliaCon, but the same basic ideas happen largely independent of frontend. So here we have a relatively simple CUDA kernel on the top right. Notably, if you want to go ahead and compile this, again, independent of whatever language that you're working in, it has to, this compiler must separate out the host code, the code on the CPU that actually goes ahead and calls the kernel from the actual device code itself, which is what you actually want to go ahead and run on the GPU. Now, part of the reason why this is the case is because the low-level LLVM representation can only permit one sort of like instruction set for the entire module. And obviously your NVIDIA instruction set or AMD instruction set is going to be very different from your host instruction set. Um, this is rather unfortunate because it means that at this point, when the compiler looks at the code, it has no concept of parallelism. In fact, not only does it not realize that it's going to go ahead and inside of that CUDA launch call something inside of a parallel for loop, when you look at the device code here, the for loop on the sort of outside is entirely gone. So we don't even know that this is going to be called multiple times. And this sort of separation between we logically know that this is going to be run in parallel with all the sort of high level semantics with it, and what the compiler and thus the runtime system actually see is relatively impactful for the ability to go ahead and optimize the program. In particular, we have some nice pieces of work that we've built over the past couple of years. We have the ability to explicitly preserve both this host and device context in one place. The first iteration we did of this was a tool called Polygeist on top of C++, though now we also have a sort of reactant plugin for C++ as well. And of course, the reactant.jl Julia package that I recommend everyone see the wonderful sets of JuliaCon's talks on this that we've had over the past couple of years. Basic idea, just like we had originally that relatively simple normalized kernel to begin with, we want to directly go ahead and embed the kernel with a notion of parallelism that preserves the fact that we understand that this is now a direct parallel loop. In particular, this enables optimizations between, say, the caller and the kernel itself, enables potential parallelism-specific optimizations. All of this I will talk a little bit more about later, but as a quick example on this code, we can potentially move this sum call outside of the entire logical sort of parallel for loop since it's computing one thing or the same thing across all these individual threads, potentially reducing dramatically the amount of work that's required to be done. And for those of you who like taking derivatives, all of these types of optimizations that we want to go ahead and perform in the primal have an outsized impact on that as well. So if we want to talk about how we go ahead and actually represent this sort of arbitrary GPU kernel inside of MLAR via Polygeist. In particular, we have an outermost parallel thread that goes through all of the blocks within a grid. We then have within there a sort of local allocation for shared memory. This is because within an individual block, the shared memory is shared across all the individual threads. This is actually a very important distinction between how the lower level LLVM representations denote shared memory. By default on these other representations, it has it as just one global that is potentially touched by any individual thread, which means that there's no notion that a change is going to at most propagate to a particular thread group, and instead is just seen as an arbitrary write that can touch any memory. And within there, we then have a parallel for loop for all the threads within a block, and finally a relatively nice version of synchronize. Now, synchronize is actually a relatively important construct when you're doing GPU programming. In particular, if you have this little code snippet here on the right, the guarantee of a synchronize is such that all the threads within an individual group have completed executing the code before the synchronize, before any individual thread after the synchronize begins executing. It turns out that, again, unlike the traditional stop the world, we want to make sure that the compiler does not accidentally introduce a race, but also historically compilers has represented synchronize as a stop the world, no optimization anywhere around this is allowed to exist. We were able to come up with a relatively nice proof that says you can get the same observable side effects that happens before relationships of async threads by just having the sync, denote a particular load and store into memory. In particular, it has the union of the read and writes of the code before, as well as the code afterwards, which enables us to, on this code snippet here on the right, realize that, that Fibonacci doesn't touch any memory. So we can, potentially move those two Fibonacci calls to be one sort of call at the top and reuse it afterwards, or vice versa. If it's actually more beneficial to go the other direction, we can split a single call to Fibonacci and duplicate it across that synchronize barrier. Now, in practice, these things are extremely useful. So here, from the original sort of Polygeist GPU papers, we ran this on a large set of different GPU benchmarks. And it turns out that most of the time when people go ahead and write GPU programs, they like being safe. They like guaranteeing that there's no possible way that their program is going to result in an incorrect answer. Unfortunately, the safety oftentimes is a little bit over conservative. So here in particular, we have this sync threads at the top. And before that original sync threads, we're writing to node, we're reading from input afterwards, we're writing to waits, reading from hidden. There's no overlap in the potentially memory locations that are written to there. And thus, we actually don't need that synchronized at all because there's nothing that would, be an observable side effect by having it there. Equally so, we can prove that a lot of these shared memory loads and stores don't actually need to exist. You can just directly move them through registers. And it turns out that in practice, if you go ahead and apply all of these styles of optimizations on real world codes, we get like a 27% speed up geomean on top of this relatively big benchmark speed. And even more for fun, we went ahead and we compiled the PyTorch source code with a compiler with all this optimization. In particular, if you're even more fun, we went ahead and took the GPU code and automatically made it run on the CPU, but we actually got a 2.7x speed up over the native PyTorch backend without running all of our fancy optimizations on top of there. And there's tons and tons more relevant optimizations that are incredibly useful in practice, especially when you're not targeting one particular piece of hardware. So one of the nice things about KA inside of Julia, as well as all these sort of high-level representations of parallelism here, is that we're just talking about a generic parallel for loop. We're not talking about a parallel for loop that is specific to a particular device. We're starting in, of course, with a parallel for or kernel which is already for a specific device, but there's no reason why we can't execute the same logical parallelism on any other device. Problem is, each one of these devices have different notions of what is going to be fast for them. Even if we stick to a GPU, even if we stick to all GPUs from NVIDIA as an example, a later generation NVIDIA GPU will have a different amount of shared memory, a different max register pressure, and all of these other sort of characteristics versus a slightly older one. And thus, optimizing your kernel to fully use all of the device characteristics is going to be different from one device to the other. In particular, we're able to now, with this logical notion of parallelism, automatically, start to figure out how to, tile and schedule all these pieces to hardware. And we have plenty of, very fun pieces of prior work that show that, hey, automatic, block coarsening and thread coarsening can get, like up to 6x on existing GPU kernels. We can get like a 9.3x plus on automatic parallelization and lots of other fun things.
Thank you. All right, so we get to the evaluation of the different ways we could integrate Reactant into parallel stencil. So the first approach is to pass the entire application to Reactant. The second is to pass individual kernels to Reactant. The third approach is to optimize the application first with parallel stencil, and then pass the resulting kernels to Reactant. Sorry, it sounds a bit weird. So note now, in all what I'm going to show, for all the performance measurements we did, the problem size was given here. The reported performance is a median of 300 samples. And we always check that with and without using Reactant, we get the same down to machine precision in terms of numerical results. Okay, so the first approach, we did not go very far with that because early results already showed that it would require still quite a lot of work for our use case on the Reactant side. Then the second approach, where we pass individual kernels to Reactant, well, here's the result. We only got a 3% improvement over the explicit CUDA code. So the best approach is the third approach, where we pass the kernels of the pre-optimized application to Reactant. And so actually we only pass them one kernel because we fuse it first. And so this is enabled by doing double buffering for the fields. So we have one field for writing, one for reading, and then we swap the pointers afterwards. And fusion can be done automatically with parallel stencil, as shown in the next slides. So now that's why at the beginning I showed you this way how to write with a mask close notation, this Stokes solver. So we take now all these, the content of each of these three kernels, and just copy it into a new kernel, right? So we have now one line per kernel in one single kernel, one line per equation in one single kernel. Then we remove the fields that don't depend on the history. So the stresses and the divergence of V. We remove that from the signature. And we use double buffered fields, so field 2b, etc., for fields that are being read and written. And then with the memopt flag, I know that doesn't even require the memopt flag, it will automatically do the fusion. And compute on the fly things as they are required to have correct results. Exactly the same results as when you would have the 3 kernels. Now, doing that, we get 68% performance more than before. And the green bar is only with the kernel fusion, and the second is when we pass in addition the results to the results of the pre-optimization to reactant. The R stands for reactant. Right, so that was the first optimization. The second is this memopt flag, which has been already discussed in the previous JuliaCon talk, so I will not go into that. We use the shared memory and register queuing. And with that, unfortunately, in the newer hardware, you don't get very good results anymore. So we get here worse results than before. Now we have flags to modify this memopt true, and so we can actually remove the shared memory part of it. And so we use then only register queuing in the third dimension. Yeah, to be clear, so this avoids redundant global memory accesses. And with that, we can then get, as you see here, up to 1700 gigabytes per second. So we get 2 times over the explicit CUDA performance that you saw at the beginning. And you can see that with parallel stencil, we get some improvement, and by adding reactant, yet another good improvement. So obviously, the third approach is what's the best. And so we set the defaults right for these memory optimizations to do something different on newer hardwares than on older hardware. Okay, so here is the summary of the results. Everything that you have seen so far in one slide. So on the left of this plot, you see Tulio, Jack, kernel abstractions, and CUDA. And then afterwards, you see parallel stencil without optimization, passing it directly to reactant, kernel by kernel. And then the next result is using only parallel stencil, so with the parallel stencil optimizations. And the last result is parallel stencil with all the optimizations and passing it to reactant. And so you can see we get, as I said before, 2 times improvement over explicit CUDA. And the theoretical upper bound is still 2 times higher. So we have still a room for further optimizations. And this work so far is quite initial, and we will go further and hopefully get still closer to the upper bound. So conclusions, combining parallel stencil with a reactant can yield better performance than using either of them alone. Then you have seen, yeah, we got quite good, very good speed up already, more than 2 times. And the strategy here shown is not just for some toy applications, but really something that works for real-world stencil applications. I conclude with the future work. So we need to figure out how to handle and expose the particular things about reactant as the tracing and the constant handling, how to expose that in more complex situations, and, well, release this work. And then we will do in parallel stencil further data light optimization and so on. And on the reactant side, there will be a lot of work going on to further improve the performance. So thank you very much. That is everything. Yeah.
Yeah, so it's a kind of a combination of these two. So the question was, can you, by using reactant, access different performance that than you would have otherwise had with a vanilla CUDA.jl? In particular, reactant's able to, like I showed earlier, run a ton of sort of kernel and other optimizations that from your existing CUDA.jl is not going to go ahead and run for you because we're able to understand a lot more about how the code works. We also have a slightly different code generation pattern. So whereas CUDA.jl has to JIT a lot of the sort of CUDA kernels in together and may not have as detailed information about the particular devices, we do have a little bit more detailed information. So there are both sort of theoretical reasons why, at least for the same kernel plugged into CUDA.jl, you would not necessarily get the same performance, but this doesn't mean that we couldn't imagine handwriting the sort of lower level assembly code inside of CUDA.jl directly. It just may not be very easy to access from Julia, as an example.
Well, you need the blocking synchronization between the kernel launches if you rely on that the computations have been finished, right? And that's what we do when we don't use double buffering. Then we need the computations to be finished in between. I don't think that in this scenario you could really get to what you're saying. You need to ensure that the fields that you want to read from have been already finished being written.
I think essentially you don't need a whole device level synchronization, but you do need to have like the standard guarantee that the earlier kernel has completed, which you can get away with via some streams and other sort of processes. But we need to make sure that like something like parallel stencil doesn't attempt to fuse together these pieces without having the previous memory already written to. And we can talk more about this offline for the specifics.
Okay, thank you. Yeah, hi everyone, and yeah, that's the talk. What's new in me? And I will actually spend about half of my talk just talking about what it is. All right, so maybe before a couple of words, what we do, where by we I mean mostly these two projects where I'm largely involved, and they mostly have to do with geoscientific applications on a large scale. So this includes glaciology and subglacial hydrology, and also geodynamics and kind of Earth system dynamics as well. And mostly these numerical codes, they implement some solvers to partial differential equations on mostly on regular grids. And we target multi-GPU HPC clusters, so that's why this talk is in this session. And on top of that, recently with this GPU for Geo project, we started thinking about making this codes differentiable. So with applications being sensitivity analysis and inverse modeling using automatic differentiation and a joint method, right? So what we want from our solvers. First of all, we want performance portability, and well, this has been largely enabled lately in Julia by well packages like parallel stencil reactants that were discussed before, also kernel abstractions, and in general, this amazing Julia GPU community. So thanks to all the contributors there. And with better performance portability, we can afford better modularity because in the older days, um, obviously, when you have to optimize a specific application or a specific architecture, it's much better to do it when it's monolithic. And now, with performance portability, we can do modularity, right? So this includes more like classical things like linear solvers, um, or well, pseudo like relaxation solvers, but also when it comes to computing properties of the medium, like rheology, then we also have packages that do that. And finally, for computing partial derivatives and differential operators, we have some already some tools, including, well, parallel stencil and some others mentioned already. But kind of still, there are kind of a few things to explore there. We want diversity of methods, right? So we have diversity of applications, which kind of mathematically means that we solve Poisson, Stokes, incompressible Stokes solver. We have some plasticity. We have some discontinuous solutions with hyperbolic systems, which means that we have lots of different ways to discretize the equations, right? So we have collocated grids, we have staggered, aka MAC grids, and for them, different solvers fit better. So for elliptic systems, Krylov subspace or multigrid solvers work fine, but for discontinuous hyperbolic conservation laws, we need conservative finite differences. So, well, there is no free lunch, so we want to pick different methods that fit a particular application better. And finally, we're small groups, we need faster development, which means that we would like to generate automatically as much as possible from minimal representation. So we would like to code the physics, and then all the things like sparsity patterns, Jacobians, preconditioners, blah, blah, blah. Ideally, well, parallelism, distributed computing we want to have done for us automatically. Right, and my specific motivation for developing this package was composable operators. And kind of the simplest example, okay, how do I compute a derivative, right? And loosely, I classify two approaches. One I call, well, or typically called eager approach, where, well, you just write the code. You just compute the derivative. And if you want to make it modular, if you want to make a library of functions to compute derivative, you just well, write a function. And then, well, okay, but what if I want to compose these operators? And then the one obvious solution is just to pass an extra, the so-called callback function, as an extra argument that will be applied before you do anything. And this is approach, well, this is how, for example, Oceananigans does compose operators, but this is, well, still somewhat limited. And on top of that, it is, well, with this approach, you have to compute things at the same time as you construct them. So, and sometimes it is not optimal. So the other approach is a lazy approach where we introduce some sort of abstraction of what is, for example, like a field. It is a function that maps, well, indices to values, and if you say, okay, everything is a function that maps one thing to another, then you, yeah, if you remember Haskell talk from the keynote, this is something in that direction. So this is a lazy approach, and it gives much better composition, and it allows to separate computation from the data. And yeah, I was trying to write a package that would implement this lazy approach, but with computational mechanics in mind. And yeah, and this is well, package is called Chmee.gl. It's a package primarily for finite difference computations on structured grids, which includes different staggered grids as well. So it features lazy operators. You construct them once, and then you evaluate them, then you compute them, which allows to reduce memory allocation to store intermediate results. Sometimes it is useful, sometimes it's not, but sometimes it's very useful. Okay, so one of the, well, in my opinion, maybe the killer feature is that it's dimensionality agnostic. You can write differential operators in math close notation once in tensor form, and then you can create 1D, 2D, 3D, 4D stencils from that unified form. It has zero runtime overhead, so we care about performance. So most of the things, it happens at compile time, and what happens in runtime, it tries to as closely reproduce handwritten code. And you can inspect this, so you can check which code is generated. Of course, it has to be GPU friendly, it has to be auto-diff friendly, and it offers some introspection. So when you construct these lazy operators, you can infer sparsity patterns, compute Jacobian matrix, and do other things, at least in theory. All right, so for that, Chmee is split in two layers, one symbolic layer and one numeric layer. So symbolic part is what happens during compilation time. Uh, yeah, you define different fields, as in continuum mechanics, so distributions over space. Yeah, it can be scalar fields, it can be vector, it can be tensor fields with different symmetries and possibly uniform in space. Then you create your differential operators, and there you can, again, so it tries to be modular, so there are different formulas, including central differences, bias differences, staggered difference, etc. Yeah, there are, well, then you can create this kind of dimensionality agnostic tensorial or like vector calculus operations like divergence, gradient, curl, and finally write your physics with a somewhat, well, very close notation to mathematics. And then at runtime, you allocate your memory. So yeah, at this compile time, nothing happens. So if you inspect atcot LLVM, it will be empty body. And at runtime, you need to allocate some memory, you need to initialize it, and then you need to bind it to um, symbolic variables. So in that case, C or concentration or whatever, you bind it to an array of certain size, and then you can write a loop or a kernel abstraction kernel or feed it to a reactant, and then you can just call a compute function on it, and then it will be computed as if you wrote it by hand. Right? So yeah, because it's dimensional, it's agnostic, you can write things usually in 1D. By things, I mean differential operators, like finite differences or interpolation operators. You usually write them in 1D, and then you just want to generalize them in 2D, 3D, which, well, usually is a naturally defined operation, and Chmee supports that through this partial derivative construction. All right, so as I mentioned, we need to have staggered grids. And yeah, so you can associate fields with the different grid elements, which kind of allows to include all kinds of staggered grids, including mag grids or fully staggered or, well, anything else. Yeah, so you just pass a tuple of kind of locations per direction, and this looks like this. Okay, so yeah, tensor calculus is a new thing. So now, yeah, on the left, there are Stokes equations and compressible Stokes equations. Yeah, if you know what it is, if not, then it's just some tensors. And yeah, math formulation is on the left, and on the right is how you write it in Julia. So tensors are first-class citizens now, which makes code really short. Yeah, okay, so, but at some point you want to compute the components of the tensors, which is also supported. So there are two parallel representations of tensors. One is, well, dimensionality independent. So it's just, if you say like tau is a tensor, then it's just tau. But then at some point you want to know what are the components in 1D, 2D, 3D, and you can do that. And here, for example, yeah, so sigma, which is a stress tensor, it is an expression like that, and then when you compute its component representation, you can do it again in 1D, 2D, 3D, and get, well, formulas that some of you most likely know. Okay, so one typical application is curvilinear grids when we try to map our domain to some defined boundaries, and, well, this is useful because we mostly work with structured grids. And how it's done typically is you map your equations from curvilinear coordinate system to reference coordinate system. Here is an example of an ice sheet which is partially grounded and partially floating in the ocean. And yeah, this tensor calculus really, really simplifies a lot this conversion. So you can just define, well, some metric identities, and then you can feed them to this tensor calculus expressions, and then you get everything else automatically. And this has, well, I won't dive into detail, but this has a really nice properties. You can preserve conservation, you can preserve some kind of metric properties, conservation loss, etc., etc. So this is quite convenient. Right, so well, then finally, as I said, you can generate the stencil in 1D, 2D, 3D. So here, for example, this is that's the momentum balance of the Stokes equation, X component of it, which I lower to stencil on different, well, on a staggered Mac grid. So I pass this topological elements, IJK, and then you can just check what is the stencil. Yeah, right, in 1D, 2D, 3D. Right, so here I think I should wrap up. So performance is largely, well, it's not about CHMI in general because it just generates code for you, but sometimes here's an example of a ice flow model where we get almost like, well, 2.5x speed up just by reducing intermediate computations from this lazy operators, and we also, well, reach, well, we get close to effective to the peak memory throughput, which was mentioned by Sam previously. Yeah, also there is work in progress on automatic kernel scheduling, which again, well, Sam mentioned, so if you manage to fuse your kernels together, then you can get better results even with optimizing compiler. Well, the better the inputs, the better the output. And yeah, because now we have this abstract stencil representation, we can actually run a global optimization algorithm which finds how to group, how to reorder kernels to have as few of them with a maximum throughput and without race conditions. Right, so there is a lot of work to do. And yeah, thank you. Questions? Well, in principle, kind of there is nothing to stop it, but recently, and there are still some bugs. So yeah, in general, it's just
Yeah, so I'm going to talk about tricksy particles on GPUs and simulating carbon fiber freediving fins. So what is tricksy particles? It's a multiphysics simulations framework with particle-based methods, and it's designed to be accessible and extensible for quick prototyping, for research, for student projects, while still being performant for more than just prototyping to actually run large simulations. And what's new this year is that we now have vendor-agnostic GPU support with kernel abstractions. So what is a grid-based or a particle-based method? So for your typical grid-based method, here as an example, we have DG, which is a grid-based method for fluid simulation. And there we have a grid with fixed points in which data is stored, and then the interpolation is done by polynomials. On the other hand, we have smooth particle hydrodynamics, SPH. That is the main method of tricksy particles. And here, data is stored in moving points. They're co-moving with the fluid, so this is a so-called Lagrangian approach. And then we do the interpolation by kernel functions. So we sum over these neighboring points and have this weighting function that we apply. And these points are now called particles. So this has nothing to do with, or it's not particle physics we're doing here. These are not physical particles, they are numerical particles. So interpolation points essentially. And why do we do that? Because we don't need a mesh. So if we have a complex 3D geometry, we can just fill it with particles and don't have to worry about getting a good mesh. Also, since we don't have a mesh, it's easy to handle changing domains, by which I mean free surfaces, large deformations, everything that would be difficult with a mesh. Disadvantages, well, they are low order by design, so they have a correspondingly low efficiency, meaning you need more particles to get the same simulation quality. And with that, you can run a simulation like that. So that is a tank of water and an elastic rubber ball that's falling into it. And this would be much more difficult with a grid-based method because free surfaces, large deformation. Right, and at the algorithmic core of the method is the neighborhood search, because only just particles within a certain cutoff distance interact with each other. So it's very important to be able to find these neighbors fast and to update them in every step, because particles are moving all the time. So in practice, we use a background grid where the cell size is exactly the search radius, meaning in order to find the neighbors of a particle here, we only have to look in the adjacent cells. And in practice, we basically loop over these cells, loop over the particles, compute the distance, and then discard all the particles that are outside the search radius. And we have a package for this. It's called point neighbors. And it's a package for neighborhood search with fixed search radius, but variable search radius is in progress. And its main focus is on performance and GPUs. And speaking about performance, here's a benchmark. So our benchmarking here is the computation of the interaction forces between fluid particles. And this is the main part of the right-hand side, so the main part of the simulation, essentially. This is a throughput plot, so higher is better. And here you can see your typical workstation CPU and an RTX 5090, which is 50 times faster. That's not really surprising. So it gets a bit more interesting if we add a few HPC nodes. So now we have another CPU, or two actually, dual socket. So this is basically two of the largest CPUs available right now. And we have the largest data center GPUs. And now the difference is much smaller. The GPUs are still faster, but not orders of magnitudes faster. This changes again if we look at elastic structures, like the elastic rubber ball, because now we have to do matrix vector multiplication with 3x3 matrices. So we load more data, but we also do more compute on this data. And interestingly, now this CPU is actually in the same range as the GPUs. But in this case, this is still using the grid neighborhood search, which we don't have to use here because the elastic structures are looking for neighbors in the initial configuration. So the neighborhood is fixed, meaning we can just compute explicit neighbor lists instead of traversing all these neighboring cells. And with this, the whole thing gets 2 to 3 times faster, but it also needs a lot of memory, which is why the 5090 didn't actually make it all the way through this benchmark. And we can also now apply SIMD vectorization on the CPU because we don't have this branching with all these potential neighbors that we discard. And we can also now see a difference between single and double precision on the CPU that we could not see before. And you can look at this and it's looking great, but the question is this fast or could it get 100 times faster? So you could take a look at a roofline plot, which will tell you that no, it cannot get 100 times faster, but we're still very far away from peak performance because we have particles. It's unstructured access, it's gathers, it just cannot reach peak performance. So it makes more sense to take a look at the competition. So this is Joule's physics. It's a mature SPH code written in C++ and CUDA, and it's highly optimized for industrial applications. And when I first ran these benchmarks, I noticed that we are a bit slower, and people kept telling me, well, it's because you use Julia and not CUDA. So naturally, the first thing I did was translate their kernel. Basically, they have not only have the same algorithm, but really the same operations. And I just hacked this into our code. Like, this is not what we usually do. But we can see with this kernel, we can actually match the performance. And I think this is a really impressive result of the Julia community, that we can have a generic kernel abstractions kernel with the same performance as a highly optimized CUDA code for a complex application like this. So no, it's not Julia. if we apply this to our production code, we can see that we are a bit slower. And this is mainly because they have a few assumptions like constant particle mass, constant particle size, that we don't have. So we wrote this, and we want to be a bit more flexible for research. So that, of course, costs us a bit of performance. But this is still using their neighborhood search algorithm, which is actually sorting particles by cell index. Meaning, in order to loop over a cell, you only have to loop over a range. We usually have an index array. So we first have to index into that and then index into the particles, which is, of course, a bit slower. But now we don't have to sort in every single right-hand side. And this makes it much easier to use packages like ordinary diffie for time integration. If you look at the total runtime, that looks very similar to what we see above here. So we have basically the same slowdown. But now we can make use of the fact that we use ordinary diffie. And we can use high order time integration, which has a larger stability region. So we need fewer right-hand side calls. And with this, we can actually match the performance. So we basically have a slower implementation, but we can make up for that with faster numerics. And I think this demonstrates what I said at the very beginning. We don't want raw performance at any price. We want accessibility and extensibility with good performance. And that brings us to the last part of the talk, simulating freediving fins. So freediving is the sport of breath hold diving. So in a competition, a diver takes a deep breath at the surface and then tries to dive as deep or as far as possible, depending on the discipline. And in some disciplines, they're wearing fins. And of course, these need to be as efficient as possible because they have limited oxygen. So they are not your typical plastic scuba or freediving fin or snorkeling fins. They look a bit different. They are made out of a thin carbon fiber plate that is attached to a rubber foot pocket. And if we want to simulate these, we have a few challenges. So for one, we have a complex geometry, but that's why we're using particles, so that's not a problem. It's too complex for 3D simulation with high resolution. We only have single node parallelism, so this would be impossibly large, so we just do 2D. And the whole thing is a lot stiffer than the typical benchmarks we find for these methods in the literature. So we had to do a lot of research in order to make the simulation stable. For example, this simulation only runs if we use decoupled time integration. So we do sub-steps for the elastic structure so that we use 60 times more time steps for the elastic structure to make this feasible. And now we looked at the video of a world record dive and we tracked the motion of the feet here. And then we applied the same motion to the very top part of the fin. So only this very top part is moving according to that. The rest is flexible and is just moving in a channel of water. And I think we can get surprisingly good agreement, considering that this is an imperfect video with unknown parameters and a weird perspective, like it's not perfectly from the side. So this is better than what I was hoping for, actually. But it's still 2D, meaning we have basically simulate a thick slab of foot instead of like a roundish realistic foot. So this is creating a lot more drag. So we can take the fin and we take some scissors and just cut the foot off. And what we can do now is we can go back to the previous simulation and we can track the motion of the particles at this dashed line and then run another simulation with only this right part, only the blade, where we apply the same motion to the particles at the dashed line. And then we get this. So this is now the blue line is the simulation without the foot. And it looks surprisingly different, considering that the blade doesn't know that the foot pocket is missing, right? It's still moving the same at the same point. So this is a purely hydrodynamic effect. And we can actually see that it's getting better. We got rid of this overshoot here in the front and in the back kick. And if we look at the fluid, then we can see why this is happening. Because with a foot pocket, you can see that this big blunt body is creating lots of strong vortices that affect the movement of the blade. And if we remove it, we only get much smaller vortices at the leading edge of the blade. And the next steps are that we want to optimize the efficiency. by varying the blade length, blade thickness, stiffness profile, and in the future, when we have particle refinements, so different particle sizes, adaptivity for higher efficiency, then we also want to run a very coarse 3D simulation. Well, thank you very much. You can find us on GitHub, and you can also find our last talk from 2 years ago linked in our README if you want more information about the method. Thank you very much. Okay, so the question is, what other assumptions am I using for the simulation other than 2D? So essentially, it's an isotropic model, whereas carbon fiber materials are not. But this is this fin is made out of woven carbon fiber layers, so it kind of behaves isotropically. And also in 2D, it doesn't matter because this would be basically the twisting. Then also we do like an artificially thicker fin because the problem is we have to have a certain number of particles in the thickness. So that limits our resolution to like only ultra fine. But if we can make it thicker, but also scale the coarser simulations, like in this video, I actually made it thicker than it really is here. So this is the real thickness that I was simulating. But we can make it much thicker and get very similar behavior, which is very great for prototyping. And yeah, those are like some of the simplifications we did. So this is a 2 millimeter thick fin, and realistic is between 0.7 at the tip and 1.2 at the base. So it is already very similar to what is realistic. So I don't think the fluid behavior changes in any way. And especially we looked at the efficiency, like the input power and output propulsion values. And even if we make it 1 centimeter thick, which is like 5 times thicker than this here, we still get qualitatively very similar behavior. And we can see that even the efficiency quantitatively is similar enough to run simulations. But yes, this is close to the actual realistic thickness. So hydrodynamically, it should be good enough. No, we don't yet have support for other mesh-free methods. We have SPH, we have a simple DEM model, and we have rigid bodies, but sorry? No, it's like for now, we only have SPH as this method. We have different SPH methods, but it is designed to be like a very flexible particle framework. So it is designed to be easy to add new methods to this.
Thank you. I'm Henrik, and I'll talk to you about asynchronous field particle coupling for multi-phase cloud simulations using heterogeneous HPC. And cloud does not mention, it's actually cloud, yeah? So the ones in the sky. Here we go. So Scale Track Study, it's a European project embedded into Inno4Scale. That was a Euro HPC project, and it was basically seed money, a one-year project to develop or come up with new HPC algorithms that would scale into exascale. So we handed in 2 proposals, and we were lucky, and we got both. And I will present one of them. So here we go. Our project partner is Tropos. It's a research institute in Leipzig, and they do anything with cloud. So remote sensing, building satellites, having chambers. The interest is a cloud chamber. It's basically a rectangular box with climate control. The one with the catchy name ACDC2 is built in America. It's an 81 cubic meter chamber. And you can imagine it has a lot of droplets inside for the condensation. So 10 to the 11 droplets. And you would like to simulate it, obviously. And the reason why you would do that is there are things that you cannot measure in the chamber. You also would like to optimize your chamber design, and for that you need simulations. Why would you use Euler-Lagrange? Euler-Lagrange is basically simulating every droplet for its own. So it's the DNS for this type of simulation. You wouldn't want to use it in production or in a weather model. I mean, certainly not in a weather model, but to abstract the models that you would like to use, having a ground-based model is what you want to do. Well, problem is it's expensive and it doesn't scale. So who is involved here? This is Wiki. I'm Wiki. I'm not a lone Wiki, but it's a small company. We are specialized in innovative numerical simulation techniques. So people come to us with some equations and we implement them for them, primarily in open form. So we are quite heavily invested in open form. And we focus into computational fluid dynamics and continuum mechanics, I should say, and HPC. I also touched on Leibniz Institute, and they are a non-university research institute, and they do anything with clouds. So they fly through them with planes, remote sensing, laser diagnostics, chambers, whatever, which is quite nice. So the objective was to use to keep using OpenFOAM for the Eulerian phase. The reason being, well, they know the code, they modified the code, it has all the thermodynamics, and making a scaling HPC code is a lot of work. You don't do that so quickly. So that was the premise, and the idea was, okay, so how can we combine that with scaling, and well, so the logical idea is, well, put the Lagrangian phase on the GPU. That's trivially parallelizable. It's wonderful. The particles don't interact. Perfect. Make that performance portable, and also have a CPU thread so you can do testing and check out some new novel algorithms, which is in our case asynchronous chaotic coupling between the Lagrangian phase and the Eulerian phase, and put in mass, momentum, energy transfer so you can do a cloud. Right. So if you don't know Eulerian Lagrangian tracking, so here's a little idea here. The Eulerian phase is your favorite CFD solver. It doesn't have to be finite volume like OpenFOAM, but could be whatever you like to solve Navier stocks. And the Lagrangian is just shooting some particles through that grid. So you need to find out which cell you are in. You could interpolate or not. Doesn't matter. The question is, how do you parallelize? And the typical way would be you have all your Lagrangian particle on the same domain, on the same processing element. Well, that means when it leaves, you have to give it to the other domain. It gives you also all kinds of load balancing problems. So we wanted to try something alternative, something radically different for the purpose, obviously, for the call. So here's scale track. So in scale track, we do it differently. We put the particles in chunks. So basically 1 million, 1 million, 1 million, something like that, and put those chunks onto the GPUs. And now the question is, how do I bring the Eulerian fields to the particles so that I can track them on? And also you have to bring in the sources because there's drag interaction, so you need to bring the sources back. And in the classical system, they would be synchronized. First you do the Lagrangian, so it's some sort predictor of your source. Then you do the Eulerian. Then you do synchronize, you do the particles. And as long as you are on the same processing element, computer, well, that's fine, yeah? Apart from the load balancing and pushing the particles around. But if you think of leaving open form on the CPU, if you keep doing the same thing, you are dead because you're moving all the data, Eulerian data. I mean, you do the Lagrangian. You will copy a lot of data, obviously. So, well, the idea is you hide it. You hide it under the computations. That's why you want to do that asynchronous, and I'll come to that. Right. So, dynamic load balancing. I'll skip that one. In the sake of time, fully asynchronous coupling. So the first thing you should note is if you do it sequentially, this is not accurate. This is state of the art. You do Lagrangian, you do Eulerian, but you should be looping over it. Well, nobody does that because it's just too expensive. And doing it coupled, it is very intrusive to your CFD code. There is examples of that, but nobody does that. So basically, if you'd say, okay, but if I do it chaotically, like I take the data I have and just do my Lagrangian tracking, and I give you back the sources, and you give it back whenever I feel like it, well, that's an error. Yeah, of course it's an error, but there is an error with doing it sequentially as well. So that would be the base. And we compared several strategies. And if you take that plot, basically the lines on the top, you basically, if you do it naively, you get an order of magnitude. You lose an order of magnitude in accuracy. But if you do a predictor, you come back to the error that you had. And physically, that corrector is, well, first of all, you take the source and you calculate the deficit. So how much didn't I put? And you correct. Basically, you keep total momentum in mind, and you basically that's your ground. You don't want the momentum to go up. It might be in the wrong cell, but it's a Lagrangian method, yeah. So is it here or that? How much does that really matter if you have 10 to the 11 particles and a lot of cells? So that was that, but you need to do something like that. Otherwise, it's hard. So execution flowchart. On the top, on the bottom, you have the GPUs. In between, you have the CPUs. And it starts synchronized up to sort of 1/3 in the middle. And then from there on, you see that the Euler and the Lagrangian, yeah, so in the second half, that the Euler and Lagrange is happens at the same time. We can also have evidence for that from NSide. So it's not just a pretty picture. That's how it should be. We looked at it and it works. Here's a plot for the verification on the ACDC. That's 81 million. So that's what you will see from here. So for the whole thing, we have only 24 million cells in CFD, which is rather small for my taste, but that's what Tropos is using. And the scaling is on the right-hand side. This is Mare Nostrum, which is quite good. So we went up to 256 GPUs. And we have also tried different arrangements because now you have some freedom. You can use you can make it strong scale and weak scale, but essentially you have two problems that you have to scale. So there is a little bit of explaining that I would need to do. We also did Lumi with similar results. And to cut things short, there is a repository, no GL package yet, but if you go wiki GmbH scale track, there is a repository, you can pick it up. We were planning to do a GL package, but we need OpenFOAM as a dependency. If you install GL and the first thing it says, I can't compile, that's probably not what you want, but we're working with Valentin to get something working. Right. It's a thin API. So if you're scared of OpenFOAM, you can plug it into your favorite CFD solver. Shouldn't be too hard. It's just a few calls. As you can imagine, Julia helped us a lot because of its tasks. Because you have all these chunks and you have to make sure that they do the right thing. And if you code that classically without coroutines in C++, it's hard. But doing the orchestration in some tasks that you can just natively run is great. Also having platform portability, it was great. So there is, everything is there. It can be extended to a lot of things, spray processes, clouds. We also have ideas to do that on a polyhedral mesh. At the moment, everything is Cartesian. Thank you very much. Shout. Um, hmm. Okay, if you look at those kinds of communities, okay, I think if you want to convert an OpenFOAM guy to using some other CFD code, that will be a hard call. Because he has lots of models, he has all the things on disk, yeah, and also somebody productive. If you look at industry, as long as it doesn't read the case, I think they will not touch it. Yeah, so you would have to write an OpenFOAM clone in Julia, and I've been toying with the idea, and it would be basically OpenFOAM on the top, but Julia for the backend. So that was the idea behind the project. Get our hands dirty on Julia to see whether we can do something with OpenFOAM. On that front, basically, it's money. I need a project to do that. I hope that answered the question. I think the answer is, I don't know, it's far away. Let's take it offline for a coffee. I mean, it's going to be a long-winded discussion. Fool me, fool me.
Maybe I will ask one. Have you been, we saw the reaction talk, and I always one of my pet peeves is how do we get things like AD to work through like we're going to work along multi-language projects like ones with C++ backends. Do you have any thoughts on that? We explored reactions with open stuff.
No, we didn't do that. And we didn't use kernel obstructions, no abstraction. No, we didn't use that, but that was primarily because we wanted to get our hands dirty. I think there the answer is yes, we should have, but then we really wanted to look at the assembly, and so we were a bit afraid of jumping into it. So there the answer is we should have. Reactant, no, we didn't. And so all this portability, but you have to see that this particle tracking is trivial. Yeah, I mean it's 3 ODEs on a Cartesian grid. We rewrote the whole solver in a week. Yeah, but that was not the aim of the project. It was for us, learn Julia. For the project was the asynchronous algorithm. And that's what it delivered, yeah. And it's a year's project, so don't. Yes, it's so much you can do. We're still fighting. I'll keep my answer brief.
Let's think of speaking more time.
So
Progress, but no success yet. Did you want to do the time? Otherwise, I can also do the time.
Yeah.
All right. I crank up like the offset as well. Okay. So.
that's done. Yeah. Well, while he's finishing setting up, I will already introduce our next speaker. So this is Boris Kaus. He's a professor of geodynamics and geophysics at the university right here where we are. So the Johannes Gutenberg University. He is interested in using computational models to understand geoscientific processes, like formation of fault zones, mountain belt, magmatic processes, volcanic eruptions, as well as, and he's also interested in using computational models to estimate the long-term stability of geological reservoirs. And of course, he's a Julia enthusiast, as every one of us, and does not only use Julia for research, but also he does a lot of teaching, a lot of his teaching with Julia. Okay, all right, Boris, don't worry about the delay. He's taking care of it. So
All right. Okay, so thank you very much. So this is about patsy.jl. It's a project that started 5 years ago together with Jeremy Kosdon. And I've had a lot of help by Valente, Hendrik, Viral Shah has been involved in getting the binaries working. So what is Patsy? Patsy is a portable extensible toolkit for scientific computation. So basically, it's a large parallel library to solve PDEs from anything from a laptop to a huge supercomputer with 1 million cores or so. It has a lot of support for finite element, finite difference, AMR. It also has time stepping solvers and ODE solvers. It was under development since 1991 or 2, so it has been around for some time, much longer than Julia. It's written in C. It has interfaces to Python and Fortran, and it also uses the backend for most of the parallel open source packages, such as Phoenix or Firedrake, or you can even use it as OpenFOAM backend. Yeah. So what did we do? Two things. We created precompiled binaries using Binary Builder with a whole bunch of additional packages, and we created the Julia wrapper, or basically the Julia wrapper had been around for some time, but we basically released it and updated it. And so let's start with the pre-built binaries. Getting Patsy to work usually is not easy, despite progress over the last decades in making the installation easier. It is still not easy, and it is therefore advantageous to have a precompiled binary that runs on Mac, Linux, and Windows. That is now available, Patsy JLL, and it has support for different flavors of MPI, including MPI trampolines, which you can link to the supercomputer to use the local MPI. We have compiled this with a bunch of additional packages such as SUDSPAR, SuperLoadDist, and MUMS, which are parallel direct solvers, hypertriangle for mesh generations. By default, we build different versions of the package for integer 32 and float 32 or complex numbers, etc. So they all need to be built separately. We also include a bunch of executables for testing, and updating this generally is not super trivial. Installing it for a user, however, is super trivial. You just go to the Julia package manager and you install it. And for the people that don't know Julia, yes, you can also run that outside Julia because it will just help you install the correct version. We have, as I said, a number of precompiled binaries that's mainly done for testing the package itself and see that it scales and works with MPI. You can run that directly. For example 19 is one of the key examples of Patsy itself to test the installation process, so you can just run it out of the box. And the key idea of Patsy is that you can add command line flags, that you compile your code once, you write your code once, and you can then from the command line play around with different iterative solvers and different preconditioners to see what works best on a big supercomputer, which is usually not trivial. And you can do the same here by simply adding these command line flags. Okay, our interest in Patsy is that we have been developing a 3D geodynamic code, and thanks to Julia and Patsy JLL, we can compile our C-based codes called LAMEM, and also distribute it in the same way. And if you have a code that's based on Patsy, that is now trivial thanks to having this binaries available. This is very useful for teaching because students can just say add LAMEM in the Julia package manager, and they have a working parallel version of the codes, and we can then use Julia to generate the input, and you run the simulations directly. And it's fantastic if you have 30 students in the class that all have a different type of computer or operating system. Okay, so that's very useful, and please use that. What about the Julia wrappers to Patsy itself? There have been a number of wrappers around, Grid App Patsy, Patsy Wrap, etc. And most of those are based, have a limited functionality, and they were only developed for a particular software to make it work in parallel. Patsy JL has been around for 11 years, but it hasn't seen a lot of love until basically 5 years ago when we started working at it again. That finally resulted in release 0.4 January this year. And I'm now happy to announce that we created a low-level interface to basically the whole PETC library, which is over 3,000 functions with automatic code generation. We also have a high-level interface for a subset of these functions, and that makes it easier to use it from Julia. We have tests for everything, and we have every function documented. And the way it works is that you have Julia callbacks for the residual and Jacobian, so the C library calls back to Julia, and I'll show you how to do that in a moment. Okay, so test, we have a test for the high-level interface, up to 58,000 tests that run in the CI. That includes MPI test and all the examples that we show. How does this work? Simple. You start Julia. You define, in this case, if you want to have the steady state diffusion equation, we define it like this. We define a PETC matrix with the correct size. Then we set all the coefficients just like you would do that in Julia. At the end, you assemble the matrix. Then you assemble the right-hand side factor with the boundary conditions, and then you set up your linear solver. There are command line options with which you can change the solver itself. Here is a Jacobi preconditioner, and then you just do backslash, and it will solve the system of equations. Okay, and that will give you a linear solution. How do we do this with nonlinear equations? This is a very simple example of two nonlinear equations with two unknowns. Same way, different is you need to set up a residual function that codes up these two equations, and you need to provide the Jacobian. In this particular case, the Jacobian is simple, so we can do it by hand. But if you want, you can also use automatic differentiation to get your Jacobian and your sparsity pattern and use that inside the code. You then tell PETC that these are the two functions for the Jacobian and the residual, and then it will solve and give the correct solution. We have lots of examples to show you how the package works with the different DMDA, DMStack, nonlinear solvers, time-stepping solvers. We show you how to use automatic differentiation as part of this and how to run all of this in parallel. Just to give you a few examples, example 62 shows 2D or 3D unstructured finite element code that solves the viscoelastic Stokes equations, where the tension stiffness matrix is obtained by automatic differentiation. This is a case where we simulate how magma moves in the lithosphere. That is 1D, 2D, and 3D. This is the 1D example, and this is a set of two coupled PDEs. And we use automatic differentiation to compute the Jacobian, and you only need to code up the residual function for this. It's very simple, and we have a zoo of solver options available. Filippo, as a PhD student here in Mainz, has been working on a code with which he simulates the generation of earthquakes over geological timescales. And the interesting thing there is that you need to go from a time step from about a year to about 0.1 seconds when the earthquake actually happens and ruptures the fault. So we got a huge variety in time stepping, and that is solving kind of Stokes equations with very nonlinear solutions. On Monday, we gave a workshop on using Julia for HPC, and we had the Kahn-Hillard equations as an example. Ivan showed how to solve that with Shmi. I showed how to solve this with PETC. Now we are 2 days later, and I had 2 full days time to use Claude to write an interface between the two. So now you can actually write in Shmi your governing equations. It will then generate a stencil, it will generate a Jacobian for you, and it will run in parallel and with multigrid solvers and with Newton solvers. So it's all combined, and this is quite neat, I think. So how do we run this on an HPC machine without having to compile PETC? Because in many cases, it's a little bit complicated to install PETC on these big machines. This is an example where I take a 3D Poisson equation, and I have 3 different curves. The black curve is example 45 of PETC, and this is a C version. So this is just compiled native C version. And I run it here from 1 node to 512 nodes, and 512 means 32,000 processors. This is a weak scalability plot, and it scales reasonably well. The blue curve is the local, not a red curve, is the locally compiled version of Patsy. So I have compiled Patsy on that machine and then just use patsy.jl and say, okay, use that, but I had to still compile it manually. You can see it works reasonably similar. And then the blue version here is now the pre-compiled version of Patsy, where the only thing I do is I tell MPI trampoline, hey, use the MPI on LumiC instead of MPitch or something like that. And that turns out that it works really well. And as you can see, it is a little bit slower, but it is not super slow. And I would argue up to 4,000 cores, you get a pretty good scalability. So basically, you can run Patsy-based Julia code out of the box for any practical use, I would say. We never, or we rarely do production runs at higher resolution with our C code. Okay, last question, what about GPUs? Can we combine this with GPUs? And the answer is yes, because we can write the residual routine using kernel abstractions. And the big advantage of that is that you can then deploy it on all flavors of GPUs. Patsy itself has support for CUDA and AMD. And so you need to configure Patsy with GPU support, but then you can directly link it and have all the solvers up and running with GPU. And to really get performance in C, you need to write your residual routines in CUDA or Cocos. And that is much easier in Julia because we can use kernel abstractions. You get a good speed up. This is an example as a 2D driven lit example. And the CPU resolution here took 400 seconds, and the same on the Grace Hopper GPU took 4.5 seconds, so it's a 100-fold setup. But then, so it's a bit difficult how to compare the numbers. But if you run this on 32 cores, then you still get a decent speed up for the linear solver. The nonlinear solver is not quite as good, and also the initial coloring stage of this particular example is still serial, so it's not super fast, but can probably be improved in the future. Okay, so to wrap it up, what did we do? We have Patsy JLL precompiled binaries, and we have a very complete Julia wrapper for Patsy. I would argue that it's much easier to write Patsy codes in Julia than using C or Fortran. It works nearly out of the box on big machines, and it can be combined with GPU coding in Julia. If you are interested, help is welcome because we have only part of the library that has high-level functions, not the full library yet. Thank you very much. Yeah, it's the pre-compiled version has an interface to the Hyper and multigrid solver. Yeah. You can select this on the command line. So you can just use the Hyper geometric algebraic multigrid solver as one of the solvers.
Maybe I'll follow up with, I think, an implied question there is, so you said for all practical purposes, you don't need to build Patsy anymore on those machines.
Unless you want GPU support, but yes.
Unless you want GPUs. So that includes, Patsy not only as Hyper, but like all these other dependencies, all these other solvers. So you put all of that into JLL as well?
Yeah, well, we have limited, not everything. So Patsy is huge. So if I go back to that, I show you what. So what we have is Suitspar, Superludis, Mums, Hyper, Triangle, Tetgen at the moment. Yeah. So if someone is heroic and wants to add additional packages, that would be fantastic. But it's usually a pain to get the binary builder things building. So it's a non-trivial exercise.
Hello? Hello? All right. Hello, everybody. I'm here to talk about a project that we've been working on for the past year or so called Spry. Um, uh, so the package is high performance networking middleware, essentially written in Julia from scratch. I wanted to quote John F. Kennedy here real quick. We choose to write our own network middleware in this decade and do the other things, not because they are easy, but because we thought they would be. So that sort of is the story of the project so far. So as an outline, I'll give sort of what we want for an HPC networking middleware library in Julia, or what at least I want and Johannes wants. Then I'll give a little bit of a peek inside what MPI does and some of the potential performance issues that causes, sort of at the limit of what MPI can do, because MPI is an incredibly fast, well-tuned library. Then I'll sort of share what we planned to do to address this, a few of the things that went wrong with that original plan. And then I'll discuss two packages, which are in various stages of working. Spry.jl, which is the networking middleware, and a little preview of my primary project at Princeton, a distributed programming language called Petrichor. And then if anybody has any questions, I'm also happy to talk later at the poster session or throughout the week. I know I'm already planning to talk to a few people. So what do we want out of HPC networking? We being at least Johannes and I. There's probably plenty of other viewpoints. And the first thing is access to the high performance networking fabrics like Slingshot, InfiniBand, and the upcoming Ultra Ethernet standard. The next one is semantics that sort of harmonize with Julia. And I'll talk about what those mean here in a second, what that means here in a second. We can achieve actually pretty good thread scaling in terms of communication performance. Recent papers at Supercomputing and a few other conferences have shown that, traditionally you used to have to use multiple processes per node in order to get the best scaling out of MPI. But with more modern techniques, we can get pretty much perfect thread scaling if you're sending hundreds of thousands of messages or millions of messages per second. And in order to fully saturate the NIC, you have to access multiple threads. What originally started the project was the ability to do dynamic wire up and participant changes. So wire up is how different processes in your program exchange addresses, and classic libraries like MPI, OpenChmem, even Chapel, the very famous networking language or HPC language, do not really support dynamic workflows. And then I want, especially a programming model that makes experimentation with different network protocols, different ways to write collectives very easy and ideally interactively, which is something that's very hard and we definitely haven't achieved yet. And I also want to give the Chapel guys some stronger competition. They sort of dominate the language space in terms of languages that are dedicated to HPC, and I think we can change that. So what do I mean by harmonizing with Julia? The first one is that it works sort of natively with the goal is that this middleware would work natively with the tasking and scheduling universe in Julia. Right now, MPI.jl certainly doesn't. Something like Rezo, the HTTP library that I think Jacob Quinn presented earlier this week, would be similar to the goal that we would have for this project. Something that natively understands Julia types. If you've ever tried to deal with complex types in MPI.jl, you'll have experienced why that's pretty nasty. MPI.jl, of course, you're making pretty high-level calls like collectives, and you have no chance to inline, do optimizations across the sort of middle layer of those calls before you get to the actual networking drivers. And I want to make a lot of things accessible programmatically in Julia. So process management. If you're familiar with MPI exec or something similar like that, you know that process management happens outside of Julia rather than inside of Julia. We have cluster managers.jl, but that's kind of forcing itself on top of Slurm on most clusters rather than really integrating with it. Job launch similarly, transport selection, you pretty much don't do an MPI, it handles that for you. And making progress, so communication progress, happen natively in Julia. And I'd also like to provide enough information for Billy to do dark magic optimizations with something like Reactant in the future. So I mentioned dynamic wire up. What does that mean? There's kind of this quadrant from a paper in the late 1990s. At submission time, most of the time, your number of nodes, your number of processes is decided by the user. That's traditional HPC jobs. That's rigid wire up, or sorry, rigid process management. If you do, submission, you submit the job, but the scheduler decides how many processes it gets. Sort of, you tell the scheduler, I can accept between 6 and 50 processes. That's what we call multiple scheduling. Slurm these days can handle both of those things pretty well, and you can probably do the same with cluster managers. But during execution, there's pretty much nothing, right? If you're programming traditional MPI, if you're using TAPL, these things are very difficult, if not impossible. Checkpointing, like with Mana and things like that, can get some of this done, but not much of it. So evolving means that the app, whatever your application is, requests additional resources or releases its own resources. If you have done all of your major computation and you're just doing some small post-processing on a single node, you can release the rest of your nodes, and vice versa, for a pre-processing step. You do a bit of pre-processing and then you request a ton of nodes, and within the same job, you get to keep that job alive. So that's what we originally wanted to tackle here with scheduling, was evolving and malleable jobs. And as I mentioned, I want to do sort of easy experimentation as much as I can in the REPL, which is very hard to do, right? If you're doing communication that errors or something like that, you can easily introduce deadlocks, hangs, corrupted state. So these are goals that I'm talking about here, definitely not something we fixed. But one thing that we can do today is take advantage in Spry, take advantage of all sorts of NIC and transport specific flags and capabilities and optimizations. And you can get very low level, at least with certain transports. You can call pretty much directly into the network driver, and that's something I enjoy experimenting with and trying out new optimizations. I want to take a peek kind of into what MPI does today in its sort of most performant configuration. So if I have a bunch of threads, 4 threads, and each of them want to do communication, they first all pass through a sort of hash check to assign them to what they call a VCI. It's essentially a virtual communicator that's internal to MPI. Each of those communicators handles matching and progress internally, but there are a lot of serialization points. So ordering is the serialization point, right? MPI implies a very strict ordering on messages. Wildcard matching is a huge source of performance issues in MPI. It pretty much serializes across all processes. And then progress is a sort of blocking call when you say, wait on an MPI request. That causes contention across every single one of these VCIs. So there's not really true parallelism happening here in a lot of places. There's a lot of issues with truly accessing all of these NIC hardware contexts at the bottom, in hardware and low-level software. And these are known issues. MPitch has spent a lot of time, and OpenMPI has spent a lot of time optimizing these things. And there's been papers on, optimizing the instruction count of a send in MPI in MPitch within an inch of its life. As few instructions as possible. But it's very hard to escape the high-level semantics of MPI. So why do we not want to use MPI and GasNet and OpenSHMEM as our backend in Julia? Lots of people have tried these things, right? I think there's a GasNet project in Julia right now. We obviously have MPI.jl. I think somebody has worked on an OpenSHMEM related project. Valentin Sharavi did a lot of work with GasNet earlier on. And the first one is none of them support true dynamism, right? As I mentioned, none of them can be evolved, none of them can be malleable. And as much as the HPC community has tried to fix that, it's a hard problem to solve. And at least I am, and I think Johannes too, is we're a bit greedy, and as many groups in the Julia community are. And I think we'd like as much of this to be in Julia as possible because we like Julia. So what was our plan to address these gaps, these problems in the HPC space? MPI and its friends, the legacy communication programs and languages like Chapel are built on top of libfabrics and UCX. Those are two kind of very low-level networking middleware programs, libraries, and a coordinator like PIMX. Those three libraries kind of form the backbone of OpenMPI, MPitch, without PIMX necessarily, OpenSHMEM, Chapel, all of these libraries rely pretty much on these three libraries. Older versions of PIMX, PMI2 and PMI1, if you're familiar with those. And our hubristic plan was to use these libraries directly instead of going through a higher level interface like MPI or OpenSHMEM. So yeah, we can abstract using libfabrics across Slingshot, Ultra Ethernet, OmniPath, if you're familiar with AWS EFA. UCX is primarily used for InfiniBand, so if you're in an NVIDIA environment, we can abstract across those, and we wanted to use PIMX to manage processes and interact with the scheduler like Slurm without having to call into the command line. So what went wrong? What got in our way? There's a lot of things. The first one is that all three of these libraries, as you might expect, are incredibly difficult to hold correctly. If you look at them the wrong way, if you access a part of it that the creators didn't expect you to access, you can get into a lot of trouble. They're absolutely filled to the brim with dead code paths. So things like OpenFabrics interface, libfabrics, you can go to the docs and you can find dozens of features that you expect that you have to handle and nobody ever implemented. No vendor took it up, or if they did, it's in a deprecated provider. But they're still documented, and sort of as you're trying to implement your wrapper, you expect that you have to handle these things and you struggle to figure out why they're not working. UCX and OFI also have dramatically different progress semantics. So if you're familiar with how progress works, right, when you make a send call in MPI, something has to drive the progress of that communication to completion. UCX is I guess, pull-based kind of semantics, and OFI is push-based. So OFI uses maybe I got that backwards. OFI uses a queue, and UCX uses callbacks. And they have very different semantics about what you can do in callbacks, and how queues work, etc. So we started with OFI. I did a fair bit of work with UCX actually before that, but for this project started with OFI, and thus far have not made it to UCX because these are very different programming models. And a lot of the documentation for these packages is really perfunctory. So, there may be very minor comments, or like I said, if there's deprecated features, like scalable endpoints, GPU triggered ops, or triggered ops, there might be design comments for these things and documentation for them, and they don't exist. And then the features that do exist are not really documented. And then the bigger issue is that PIMX can support the dynamic jobs that I discussed earlier, right? Malleable and evolvable jobs. But nobody else can. There's a chicken and the egg problem because PIMX is designed to support these things, but Slurm has never and may never support these jobs. And so we implemented support for PIMX dynamic jobs, and then we can't run them because there's no scheduler that can handle these kind of jobs. Even more arcane schedulers like Flux from Lanol, yeah, Livermore, are intended in their papers. They write a lot about evolvable jobs, malleable jobs, but it's never implemented because no packages or libraries need them because it was never implemented. And so this is a really big problem. All right, so where are we at now after all these missteps over the past year? We've taken a lot of inspiration from a middleware library called LCI out of UIUC. It's built for asynchronous multi-threaded runtimes like Parsec and Charm and HPX. It has a fairly limited interface, which is very nice, much more limited than UCX and OFI, especially OFI, but it's pretty much just as expressive. It has a lot of different completion mechanisms, explicit control over resources, and it is very, very, very fast. Compared to MPI, you can get significantly better throughput and much better times per step on fairly large machines, 100 plus nodes. Most of this performance comes from their extensive use of atomic data structures and their very explicit avoidance of any synchronization points across threads. There is pretty much no point at which you have to serialize a send or a receive or anything like that for matching, tag matching, and similar things. So pretty much each thread gets its own communication context and is fully separate. I think these are a little bit out of order here, but I'll talk briefly about the performance just so I don't run out of time. With Spry, we can get pretty much perfect performance for scaling threads. This is still very small benchmarks, but we can scale pretty much up to the line rate of a medium-sized InfiniBand cluster. We obviously are much faster than TCP on the same cluster. We pretty much match the native bandwidth if you were to write this in C. Yeah, so performance is very good thus far in testing. So how does Spry work? There's a global context, which effectively just acts as a cache for various objects that applications might want. And then from there, it contains cached fabrics and cached endpoints. Cached fabrics are essentially, your interface to InfiniBand, or your interface to shared memory transport, or your interface to Slingshot. They're cached because one application might want to use just RMA, and another application might want to use tagged sends. They will go on a single thread, they will go through the same endpoint, but they're correctly typed at the application layer. So there's an untyped cached fabric. Untyped is a strong word, but untyped for the purposes of the capabilities, and then a typed version that applications get access to. The same thing with the endpoint. The endpoint is the primary unit of parallelism. It's where you'll send, it's where you'll receive. And then there's a couple other objects. There's really not many objects in the design. You have objects for peers and a resolved peer that has 0 lookups, and then you can register memory for RMA and atomic operations. There's also not that many verbs in the interface. We have peer-to-peer, so send, receive, tagged peer-to-peer, so tsend and treceive. The nice thing that we sort of learned from LCI is that you should avoid hardware tag matching at all costs. Right? We have these NICs that have very powerful hardware tag matching engines, but those tag matching engines use the MPI semantics for tag matching. And so they are a pretty significant serialization point. If you run this in software, LCI found that the thread scaling was pretty much perfect. And so we allow you to use hardware tag matching if you expect it to be good, if you don't need the maximum performance for tag matching, but software tag matching is the default in Spry. RMA, atomics, and a few control functions like progress, wait, wire up, and register. In order to do certain things, like for instance, if you want to inject a message immediately into the network and then get back your buffer without asynchronously waiting on a completion, you can essentially just wrap the buffer. So it's kind of that's how you do options is with very lightweight, hopefully not combinatorially explosive wrappers on the buffers. You always get a return immediately. It's asynchronous. Every verb in the package is asynchronous. So you get done if it was finished in place, posted if you need to wait on a completion, retry if there's back pressure. You need to spin and do some progress. You need to try another thread, perhaps, which is safe but low contention, and failed in the worst case. I'm going to move on a little bit quickly. So compared to the worst case of MPI, where there's essentially one lock in front of the NIC, we pretty much get access to the NIC for every thread independently, up until a certain number of threads, at which point your NIC has exhausted its hardware resources. I'll skip past the end-to-end resources. I think I have the exact same slides there, and I want to talk briefly about Petrichor, which is my sort of likely PhD thesis at Princeton. The core here stands for choreographic, and petrichor is the smell of rain. So what if we tried another global view programming language, right? We've had X10, Titanium, Chapel, Co-Array Fortran, or not Fortran, High Performance Fortran. And so what if we tried again? It didn't work out for those other people, but it could work out for us, right? But we do believe that there's a couple of reasons for this. So choreographic programming is this essentially idea that each value has with it a location in addition to its type. So there's kind of a tensor product between the type space and the location space. You have these explicit arrows. They're kind of the squiggly arrows on the screen. So A sends 2 plus 3, which is a pure computation, so you could optimize it away, but whatever. Sends it to B. C does some computation and also sends it to B. And then what happens is we take these variables and these arrows and we project them out into 2 separate static programs. So A runs a program that only does the send, and B runs the program that only does the receive. And this comes out of the programming languages community. And the nice thing that you get about this, with this, which is different from Chapel, which is also a global view programming language, you get deadlock freedom completely for free. So you will never be able to accidentally program a deadlock into your program. Here's an example with typed values instead of just pure computation. This is in a purely functional form. This is not how it would look in Julia. And the idea here, like I said, every location has a type and communication is explicit. We have this choreographic arrow. One of them is a point-to-point send, one of them is a reduction, and one of them is a split. And those are the 3 fundamental arrows. And they can be used to express in a single place every single MPI collective. And I'm done. No, so we're still trying to do benchmarking and performance tuning for just sort of within the library still. Hopefully, I'm trying to finish by the end of the week some more benchmarking against like MPI.jl. I will say versus distributed, for instance, I have done that testing. It's absurd, but the 0MQ? No, I can give that a try. I don't know. Is there a 0MQ wrapper in Julia? Okay, yeah. Yeah, I can give that a try. Yeah, I'll let you know. Trying to get it done by Friday, or at least into a 0.1 state. There's a few more bugs to fix before it's even like viewable, I think. I'll send out some sort of message on my own feeds, and it should be available there. Yeah. Yes, actually, so I'll probably announce on a blog of my own or something like that, and then once this is out, that I would like to solicit testing on your clusters. I'll put together a benchmark repo, and I would like to give things a try across a lot of different configurations. I've tested on Perlmutter and Tiger at Princeton, but that's it. And those are two, yeah, only 2 clusters out of hundreds.
All right, our next speakers are Jan and Felipe. I don't dare say Jan's name because I don't speak Brazilian, but you can see it certainly on the slide. He's a software engineering student at the University of Brasilia. And Felipe, he is a consultant at MIT's Julia Lab, and both work on Dagger.
I was prepared for giving myself a presentation and yeah, a presentation, but thank you. It helps a lot to not explain yourself and what you do. Um, but basically, we're presenting the combination of a 3-year project on Dagger that's bridging the gap between the runtime and its HPC interconnects. So the overarching idea when we started 3 years ago with my Google Summer of Code project was there are known problems with networking in Julia, specifically with distributed.jl. We have James Wrigley that is creating distributed next for a plethora of reasons and other distributed JSON packages. So why not include MPI as a backend of Dagger instead of only distributed? And this took us on a 3-year crusade of adding a SPMD interface to something that is inherently RPC based. So again, the overarching idea was keeping Dagger's productive task API, its automatic array distribution and execution of code throughout multi-node, multi-GPU, and multi-core, but also meet the machine and the ecosystem where it's at. So adding MPI, but also adding an interface for future developments of probably UCX, BGS, Nickel, Rickel, and etc. And the idea was doing that and enabling it within the runtime with a single line of code that you can see on the screen, dagger.accelerate bang MPI. You can use MPI out of the box with the runtime. Ian will explain a little bit further about how that works and how can you use it.
Yeah, so thank you. So here we have a simple example showing how we can use the distributed backend and the distributed MPI in Dagger. And you can see that it is not like a big deal to change the backends and make that changes. You just need to change the distributed and for the MPI, and you define it how many ranks do you have on launching the program itself. And like the the great idea of Dagger is if we can write parallel programming serial, so you don't need for thinking of how the communication protocols, all the distributed pane that we have. And here we have an example of Cholesky implementation. That on the left side we have a serial implementation using BLAS and other things. You can see the loops itself, and you can see how you executed that, for example. And in the other side, we have a parallel implementation using Dagger for that same specific Cholesky. And we can see that the difference between them is not that hard. Have some points that change, for example, the dagger dot spawn that spawns it as a task, because the whole point in here is to uh, define the program as a task based. So yeah. And in here we have another example of the same Cholesky, but it was written all using MPI. So it's interesting because when you deal with MPI and other protocol communications, you will need with broadcast, you need to send and receive message, you need to handle all these problems inside of the algorithm. So you need to think about the problem that you're handling and also the communication side of it. So yes, it's totally possible, but if you like just can think about the problem itself, not how it will scale in parallel, it will be more worth, for example. And also we had it integrated with GPUs using GPU aware. And it is also quite simple. When you instantiate the GPU on the program, it is not like forgot the word, but you don't. It is not automatic. Yeah, that is the word. You need to create a scope of the GPU, because when you specify the scope of the GPU that you're using, you also you can pass the tasks on that GPU. And here we have like it's very simple. You just need to create the Dagger scope, Dagger with scope, and pass the scope, and you pass the tasks inside of that scope. And in here we have a comparison between using distributed GPU, and also MPI plus GPU, because we can like use all together. Like imagine like you have a problem and you want to use distributed for, like for example, for AWS and a GPU also. So and after that you, oh okay, so I had get access to an HPC, so now I want to run it using MPI and use all the advantages of HPC. So yeah, you just need to change one line and all your algorithm will be working on HPC. Another thing is we already have some factorization implemented, dense linear algebra, extensile, and if you want to get how that extension was implemented in Dagger, we have like 2D, 3D, and all these stencils. Just get in here for the next talk. So
So the main overarching idea is, as you could see, writing MPI programs is much more than just having a scalable parallel algorithm in theory. You need to think about synchronization, think about the communication, writing that within your algorithm that adds not only overhead in production, but also it's a pain to debug MPI within the ecosystem, as we all know. Um, but again, as Ian showed, you can write any kind of algorithm that you would in serial, but with MPI, as long as you use dagger.addSpawn and annotate simple read or write dependencies between the tasks themselves. Um, Another thing is, if you're not trying to implement those algorithms, we already exposed a plethora of them, including stencil and linear algebra operations. Not only that, we also have a pretty big support on streaming capabilities and other supported interfaces. So as for results, we scaled up to a weak scaling of 64 ranks on 16 nodes of MI300As. We know performance is shorter than it should be, although we are just merging MPI within Dagger and we're coming into the optimization phase of it. Weak scaling is decent, I would say, but we're looking for users to stress more of the system and also standardizing our own benchmarks. So as I said, the idea for this is to lay the ground for SPMD communication protocols as a backend of Dagger, while still maintaining its productive API front end. So expect to see we merging UCX, PGAS, RICL, nickel, and all of those good things that people use in the HPC systems, and also standardizing our own benchmarks. So if you guys have any questions, we'll be here and we're open for them now or throughout the conference.
Questions for Felipe and Jan? We only have one microphone, so please speak loud.
Um, the, it, the question is related to MPI groups, right? Or different communicators. So yes and no. You can create an array into a limited set of rings, but you do it through Dagger's interface of processors. So going a little deep, each processor or each Dagger processor has a rank annotated within it, and you can specify to each processor each array is created or a group of processors. So they are not necessarily MPI groups or different MPI communicators, but you can create different arrays in specific groups of ranks. They're just not MPI groups, they are exposed to Dagger's API. Exactly. So you declare a task. You declare that a task will execute within a set of Dagger processors, and the Dagger processors themselves are annotated with ranks. So you say processor 0 to 5, which translates directly to rank 0 to 5. Yep. Exactly. Uh, w- that's a fair question. We are currently exploring different scheduling policies within Dagger. We talked about implementing MPI specific or distributed specific for that matter, because it would be twofold scheduling policies. Currently, it's only about the message passing itself, so it doesn't change the policies. But we expose a way for the user to create their own scheduling policies right now. So you could, in theory, create it. We are planning on adding it in the future. Very fair question. I don't know if everyone heard, but he mentioned we mentioned that it took 3 years to settle on the backends and the communication backends for that matter. How long do you expect it will take to add different communication backends? The fact that it took 3 years is because we wanted to have a rock solid interface for any kind of SPMD communication scheme, because we already had that for RPC and decentralized things. So it should take no more than like a couple of weeks to a month to add like UCX, for example, because the SPMD interface design is what took us 3 years, and we vehemently are confident that it works for any kind of SP and DB communication. So it should be pretty straightforward now. That's why it took 3 years, by the way. It's so hard adding SPMD shaped things to RPC shaped things, as you can imagine. But yeah, we are very confident in it now. Any more questions? I think that's it. Thank you, guys.
All right. Our next speaker is going to be Julian Samaru, who will give the talk together with Felipe again. So Julian is a research software engineer at the MIT Julia Lab, and Felipe, as I said, a consultant at the MIT Julia Lab.
Thank you very much, Sam. So thank you to Felipe and Jan for that awesome starter about the MPI work that we've been doing over 3 years. It's an awesome development. So I'm going to go into something that's a little bit more application directed or maybe application specific, talking about stencils. Now, we had some earlier talks today about stencils, which was very interesting and work that we're going to have to follow up on. And we'll briefly mention that in this talk. But what we want to talk about is doing stencil computations with Dagger.jl, as well as looking at other libraries like Parallel Stencil that allow you to express stencils. Before I get ahead of myself, what are stencils? As a quick refresher, a stencil is essentially a way to apply an update to an array. You have, say, a 2D, 3D, 1D, whatever dimensionality array. And for each element in the array, you want to update it, but you don't just want to look at that one element. You want to look at a neighborhood around the element, and you want to do something special with that. So maybe you want to implement diffusion. Well, you need to generate a kind of plus looking stencil where you read the neighbors as well as the center, and then you do some computation and then update the center based on that value. And you scroll, you basically do this scrolling across the entire array for all elements, also doing something special on the boundaries, which we'll talk about. This is an example of a two-dimensional stencil that you might use for diffusion or something like that. I believe this is the 2D Jacobi operator. I might be wrong. I'm not a mathematician. This is the idea that we're going with, though. So we've got in the Julia community not actually a whole lot of options. I am missing one or two that I wasn't able to find, and now I'm realizing I should have added to this slide. However, these are really the big ones right now. I think everyone here probably knows about parallel stencil.jl. That's the one pushing the boundary of what's possible for performance on CPU, GPU, and with and without MPI. Um, there's also image filtering, which is typically used for convolution operations, and stencils.jl, which is a newer one for doing things that are not just image processing. And then there's Dagger as well. And we're going to get more into the detail of what we scale to, but you note that different stencil implementations, different libraries, provide different functionality and where they can scale to. So so let's just quickly take a look at the different ways that you can actually implement stencils using these libraries. So image filtering, you can use this centered operator to generate an inner kernel that you're going to use for, say, again, a 2D Jacobi diffusion operator. And then you call imfilter with that kernel with your output array U2 and your input array U, and specify what the boundary conditions are. Now, I mentioned boundaries before. I'm going to skip over it for just a second because we're going to have a good way to actually visualize what these are, but just briefly, it's what you do at the edges. Stencils.jl, we have this thing called a switching stencil array. You specify the kernel that you're going to use using this von Neumann operator. And one is essentially telling you what is the size of the operator. Is it 1, 2, 3, etc. It changes how that operator works and how far it has to look. And you specify the boundary using wrap, which again is periodic, go off one end, come back in the other. And then you use this map stencil operator, and it's pretty natural. And you have a little bit more control than image filtering. Um, Parallel stencil is where things start to get really convenient, and of course performant, but with the syntax above, it's very nice, very easy to be able to implement the same stencil operator using these at-in macros and these very convenient derivative operators, finite difference operators, excuse me, at D2, XI, YI, etc. And then additionally, the boundary is handled, boundary and this case is just the boundary, is handled externally. And then Dagger kind of wraps all of this stuff up into this one at stencil operator, where internally we specify our kernel and we specify first our neighborhood size. So basically, how big is the space of neighbors that we're going to look at? That's the at neighbors macro. It also specifies the boundary operator. And then we take that, and that basically gives us the actual values that are within our neighborhood. And then we just do our computation and we return the final value for that element. And again, these are expressing this operation essentially as a per element operation as you run through. You're doing kind of the same thing. Okay, so Felipe, I'm going to hand this over to you.
So as you guys saw the MPI backend presentation previously, as we said, the intent of it was to expose MPI communication to any type of Dagger API that is also exposed to the user. Therefore, Stencil is one of them. I intentionally skipped mentioning it because I knew I was going to be here again. Um, but it's as simple as adding a single line to enable MPI communication for your stencil execution. In this case, you're also adding the thing that Ian mentioned previously, which is the Dagger with options, the scope, Dagger scope, CUDA GPU 1. So this will be running not only MPI, but it's running MPI in the CUDA GPU with the ID 1. So again, as simple as that. I'm gonna pass back.
So since the last JuliaCon, where I kind of gave a few examples of how to use this kind of very new stencil system, it's grown significantly. There's been a lot of progress over the last year. In particular, we've added a number of other boundary conditions, and we're going to see what these look like in the next slide. But these are useful for all different kinds of problems. If you've done stencils, you know what a lot of these are, and you know that it's convenient to have when you need to reach for them. So a lot of these are just built in and very simple to use. Additionally, some stencil libraries only let you specify boundary conditions in all of the dimensions simultaneously. It's all one or well, it's all one or all the other. Um, with Dagger, we added support for specifying the boundary conditions differently per dimension. So no matter how many dimensions that you specify, you can specify, if you want, different boundary conditions for each, or you can just say, for example, in the top right, wrap, and if you have multiple dimensions, it'll just apply it to all of them. Depends on your problem. Additionally, you can also specify the neighborhood sizes independently per dimension. So maybe you only need along X well, in this case, along X is 1, along Y is 2, however you want to say, row column, whatever. You can specify these differently to indicate that you only need a small neighborhood in one dimension, a larger in another. It all depends on what you're trying to do. Um, 5. Okay. So kind of speeding up on this a little bit. What are the boundary conditions? What do they actually look like? It's sometimes hard to tell from the name because people call things different names. But you can basically see here if this is your inner array and then you apply each boundary condition, what does that actually do once you start indexing past the edge, right? Because you're looking at a neighborhood. What happens when you get to the elements on the very edge where now part of your neighborhood actually goes off the edge of your array. And the boundary conditions basically tell you what to do. And we have different ones like wrap, which wraps all the way around, very common. Pad to a custom value, commonly 0. Clamp, reflect, linear extrapolate. Additional ones are going to be added as well. And if you have ideas for other ones that are worth implementing, just file an issue and we will be happy to add them. Performance.
As you can see, we're pretty much performance competitive with the landmark packages of Julia itself. So Dagger.jl on GPU almost matches entirely parallel stencil.jl, both on the GPU with threads, and we have the baselines of serial and handwritten as well.
And just you'll note that image filtering has really low performance. It's actually not designed for this, so that's the reason that's so low. But it is nice to see that Dagger is getting very close to the top of the line with parallel stencil. Now, of course, I can regenerate this on a different system and the values are going to move around a bit. But for the most part, this is about the ballpark that we're in. And looking at our strong scaling results, this is just for CPU multi-threaded. We're working through some issues for multi-worker and multi-rank. But for multi-threading, we're doing quite well. As we go from 1 to 16 threads in this example, we're basically able to hit the memory limit and saturate memory bandwidth, which is exactly what you want to be able to do. Yeah, very, very good sign. And then just real quick, boundary conditions don't really cost anything, so don't be scared to use the one that you need. You know, you shouldn't be worried that, oh, something might be more complex, it's gonna add a lot of overhead. No, it's not a problem. And then just real quick, we don't really have much time. We just put some fun demos together. Gray Scott example, you might have seen this with the kind of coral reaction diffusion growth. This is another configuration that Claude managed to find, which is kind of cool. Excuse me, and it's pretty simple to write. There's more code than this, but for the most part, this is the core. And then additionally a dam break, which kind of shows you as the dam breaks and the wave propagates, it reflects off the top and bottom because that's the boundary condition we set there. And then it wraps around on the left and the right. And it's quite easy to implement. And there's also this anti-reflect boundary condition that we added, and that will make it into Dagger itself. Um, yeah, so where we are right now, MPI is already added, that's merged. Hierarchical scheduling merged this morning, all in Dagger 0.22, which is just being released. But where we are, we have mostly performance optimization to do. At this point, all of these known costs, they're just, let's limit memory traffic when we can, when we know it's possible, and let's use something like Reactant, as Parallel Stencil is doing, to really get the last bits of performance out. But that's it. Thank you.
As one other remark from what Julian just mentioned, we are actively looking for users to stress our code in order to expose the optimizations we need to do and to be targeted. So if you have something you want to run that is inherently parallel and needs to be distributed, use Dagger. Talk to us. We will be more than happy to optimize now that all the backends and interfaces are completely settled.
Why not? Sure. I think we're going to start looking at more complex partitioning and indexing methodologies in the future, but there's nothing to say that you can't define your own hexagonal grid operator. Like we have Dagger's D array, which is very much designed for simple Cartesian indexing, but you could define your own that instead uses custom indexing, custom partitioning, all of that. If this is important for your use case, it would be useful to take a look at this together and we can figure out how that should look. But there's nothing to say you can't do that. But a little bit of implementation work would be necessary.
We would be more than happy to work on it. We put a lot of effort, again, pondering on the James question. We put in a lot of effort not only in NPI but also in other interfaces to make them as modular and as expensible as possible. So why not add something new? That was the whole purpose of taking the time we took to design everything. So we will be more than happy to help with it.
Any other question? All right, then we wrap up. This was our last talk, this Julia for HPC mini symposium. We hope to see you next year again, and have a good lunch.
try it again.
Thank you guys so much. Thank you. Let's try this one first. This was the one that had problems before, but maybe we'll get lucky this time. Turns out, yeah, switching.
Yeah, it takes a few seconds.
Yeah, it's a little. Ah. So okay, this one's probably a no then. Or you know what? Oh, stand by. I hit accept, and then I hit mirror.
No, but you have also the others, the
Use the station. Yeah, that's fine. Is that like as long as this?
I don't know expectation. I think we can not keep
You don't mind that. Yeah, we might see this one. Oh, do you have a render for it?
Oh, oh. Prayer, prayer. Oh, I'm fine. Nice. And the mic is working.
Sweet. Do we?
You probably have time to do the mics if you want. Okay, and I can just do a really quick announcement just for like the general stuff. So hi everybody, welcome to the GPU Mini. We're gonna get started pretty soon. Our speakers are just getting set up, and we have a couple minutes before the Mini officially starts. So just some quick logistical stuff. If you're a speaker and you haven't spoken yet, I'm gonna be sitting like right here with these time cards. So there's 4 of them. 15-minute warning, 5-minute warning, take questions now, and one.
Uh, so again, I'm Julian. I'm not Julian, actually.
Congratulations.
Well, starting off with the right foot. Um, I'm Felipe. This is Julian. Now I nailed it. Um, we're both research software engineers at MIT. I'm a student. He's a research software engineer. And we are going to talk about easy multi-GPU development with Dagger.jl. A long time ago, uh, in our perspective at least, like 5 or 10 years ago, one GPU stopped being enough for many workloads that we have. So massive simulations started popping up, the exascale project started popping up. So we needed to move to many GPUs, if we're not doing scripting, that is. So um, we needed ways to easily program our multi-GPU algorithms, and Not only that, we needed ways to do it quickly because we are inventing new algorithms that fit into this new workload. Uh, in general, if we're doing dense computations, a big flow 64 or even a flow 62, flow 32 matrix will not fit into a GPU. So those massive simulations I was mentioning will not fit into a single one. Um, if you're doing things like AI inference or any kind of AI workload, a MedMol is also threefold the size of a huge, enormous matrix, either of parameters of or of your model. Um, and even well before that, we were already moving things from the GPU to the host, from the host to main memory in order to save up space. So why not just use the hyperscalers we have available for AI?
And real quick question, can I get a raise of hands? Who's run into a situation where you wanted to allocate a problem of a certain size, but actually your machine didn't have enough RAM for it on a single GPU, so you had to actually scale down? Good number of hands.
Okay,
Okay.
so I would say at least 50%.
Yeah.
And I imagine that some of you, myself included, had access to more GPUs, but it was so hard to program and that you just scale down. So yeah, this is one of the reasons that we wanted to make Dagger both easy and scalable for multi-GPU, that is. In general, but this talk is about multi-GPU. So in
Yeah, you want me to take that?
yeah.
So the idea, so kind of for this talk, we're going to be talking a lot about the Cholesky, but this is going to apply to really any algorithm that you want to implement. You really, the thing on the left is actually really nice, right? I mean, that's not a full Cholesky, it's kind of a shortened whatever, but you want to be able to write compact code. If you want to define an algorithm, say you're reading through a paper and you're like, okay, I'm going to go implement this thing. Well, they might show it in pseudocode as 5 lines. What you write is like 100 lines, 200 lines, 300 lines. And that might even just be for a single GPU or something like that. When you start getting to multi-GPU, it gets out of hand. Because you have all of this work to deal with. It's like, okay, you need to decide where is this tile going to go? Tile, let me back up a little bit. Let me take my whole array. I'm going to factorize this. I'm going to break it into tiles. I'm going to partition it because that's naturally how you parallelize things. And so now you have the problem of, okay, I have all these tiles, but where does each one go? How do I decide that? And then once you decide that, then you actually need to go allocate it on the right device. Okay, so now you're having to do Julia tasks so that you can switch to a different stream, a different device, all that. Okay, that's kind of annoying. And now okay, so that's fine. So now you maybe do your initial first wave of computations on those tiles, but then now you need to exchange data. Okay, well, now I got to get the right context set, the right stream set. I've got to call the right transfer method. Okay, that's kind of annoying. And now, et cetera, you start dealing with peer to peer. You start dealing with like IPC if you want to do like really efficient same node multi process stuff. And then synchronization is just not fun. So it gets complicated.
Even more so, when you're dealing with either matrices, tensors, or arrays, or you name it, you are always incentivized to use the vendor packages for a single GPU. That is pretty straightforward. But again, once you get to the multi-GPU level and you try to scale up, you're kind of stuck between a rock and a hard place because Kusolver MP, for example, or Kusolver multi-device has its own issues. And if you're trying to really, really scale up to multi-process, I think that Kusolver MP is not even version 1.0. So you're kind of in this situation where you're between here and there.
Yeah, and when it's good for NVIDIA, it's so much worse for AMD, and it's non-existent for every other backend. So
Um, so essentially, you already have the algorithm in mind. You already know how to do these things. You just need to write them down in code. How do you synchronize between GPUs? How do you do message passing? Or if you're not doing message passing, how do you translate this data from one GPU to the other? Or you move it? So you already have these things laid out for you. You just need a language, not a language, but something you can express these dependencies on. So we have this easy way of annotating these things um, called in out or in out, meaning write, read, or read and write, which translates to the same dependency as a write, but
And these are ways of talking about data dependency.
exactly. So you usually your pseudo algorithm already has that laid out, or you already read the paper about your algorithm, or you're doing an application where you know which operation touches which piece of data in which way. So the most straightforward way is just saying this specific function, either this being a vendor kernel or some kernel that I wrote either with CUDA or kernel abstractions or ROCm. This reads, this writes in this piece of data, and that's it. We handle the rest for you.
Yeah, you just have to read the specification and just translate it into this form.
Uh, Honestly, I shouldn't be saying this, but I will, regardless. We're doing experiments. We don't have results definitively yet, but this also helps a lot when you give an agent, you can imagine, a paper that already figures that out for you, and it writes in this, I would say dialect. But yeah, results pending. We will publish a paper in a short amount of time about this. So, as we mentioned, you already have access to a DAG. This is the DAG of the Kolaski we just kind of showed you. So you have your dependencies laid out, you have a POTRF, and then you have this whole exposed way of doing parallelism. We are not going into scattering policies that much in this talk, but we also deal with that. So as long as you have access to these things, which I assume everyone does, given an algorithm, you can write your code in Dagger. And it has a multi-GPU capability straightforward from that.
So the the algorithm we just saw, so this DAG right here, this directed acyclic graph, in Dagger, that is implemented with this algorithm. So we show this all the time. If you've been to other Dagger talks, you recognize this because this basically has not changed in years. And that's a good thing. But this is a Cholesky factorization written in Dagger using these data dependencies we were showing you just 2 or 3 slides ago. So for example, at the top for K and 1 to MT, and then you dagger at spawn a POTRF. So a inner Cholesky factorization. You pass a few parameters for the ones where you're reading or writing data. You just let it know with in out, which is read write, or out, which is write, in for read, etc. And you notice that if you were to remove all of the dagger at spawns and all these in out things, you would have a proper sequential algorithm. You could run this on a just plain partitioned array using like block arrays.jl or something like that, and it would be a Cholesky factorization. But what happens when you add Dagger to this problem is now this becomes not sequential, but this becomes parallel because Dagger can see, oh, I can look at the data dependencies here, and I know actually these TRSMs right below the POTRF, these are all independent of each other. They do not write to the same data. They read the same data, but they do not write to the same data. So this is very, very expressive for parallelism.
And although I assume that most of us know what a Kolaski is, I also assume that most of us haven't looked at a pseudocode for a Kolaski factorization. So you guys will have to trust me in this one because I'm from the field. This is exactly the way you write a pseudocode for this algorithm. If you obviously take out the dagger.add spawns and the annotations from the language, this is basically the closest you get from the pseudocode for a parallel Kolaski algorithm, at least in my experience.
Yeah, if you go to supercomputing, you see this particular algorithm all the time.
So yeah, um, it's as simple as doing the annotations that we just showed you, declaring your dependencies, and wrapping the piece of code you want to run with either one or multiple GPUs. If you've been to the previous HPC mini symposia, this is the same way you do it with distributed and MPI. You just call it upper level different way, but I'm not getting into that now. You just wrap it with Dagger with options. You define your scope. So Dagger CUDA GPU 1 is not meaning that you have just one CUDA GPU, but you're running in the CUDA GPU with ID1 on your system. And if you want to use all the CUDA GPUs you have available, you just double dot it, comma. Sorry, I'm not in English speaker. So this is a comma. You just put a comma, and it runs in all the available GPUs you have.
Colon, not comma.
Colon. And same thing for ROCm GPUs, or you can just say all the GPUs that I have available, either CUDA, ROCm, Metal, OpenCL, you name it.
An important point here. So the algorithm we showed right here, that is behind that Cholesky call right there. That's what happens, plus a little bit of linear algebra.jl stuff, making it out of place. These dagger dot with options and this scope stuff seems kind of verbose, a little bit annoying, but the point is this algorithm right here does not specify CPU, GPU, MPI, distributed, any of that, single GPU, multi-GPU. These little annotations here transform it automatically to be, and this is the purpose of this talk, into a multi-GPU algorithm automatically, not having to think about placement, scheduling, all that stuff.
Again, if you were at the HPC Mini Symposia, you were probably fed up with me talking about this, and you should be, because sometimes it can get pretty annoying. But as long as you call these two lines of code within your multi-GPU code, it will not only run multi-GPU, obviously you need to call MPI exec or MPI exec.jl or any kind of MPI runner you have. This will run multi-node, multi-GPU. You can also choose to have one rank per GPU, or one rank per node. Your choice, your call. We handle everything else. If you want to check the uniformity of your code and you're dealing with SPMD fabrics, you can also toggle that, do a little debugging, and check out if your multi-GPU code is running, why your multi-GPU code is not running correctly if it comes to it.
Right, because we're gonna, you know, a lot of us are gonna do multi-GPU with MPI, like on a supercomputer, on a cluster, whatever. So that's a very nice tool for ensuring, okay, all of my stuff is still correct.
So for our benchmark results, because we need to start taking questions, this is the Koleski we mentioned. We are working with optimizing our CUDA weak scaling. As you can see, we still decay a little, but I think it's acceptable. We're starting the optimization phase of Dagger. We're planning on launching version 1.0 because we settled on the APIs we showed you, and we're starting the optimization phases. Although the weak scaling on an MI300A for Metmol specifically is pretty good, pretty decent. Although we can recognize that the Koleski results are due to a one GPU starved run. The part on the right is ROCm CUDA strong scaling. Our strong scaling results are pretty decent as well. So
yeah, the weak scaling for ROCm is just basically an artifact of where we draw that line at 1. But otherwise, it's weak scaling as you'd expect.
Yep.
Yeah. And then, yeah, I mean, this is more of an honest comparison or discussion of where we are today. This is all on master right now. That, you know, sometimes with really small block sizes, with really small problem sizes, the scaling is so-so. You have a lot of memory traffic, GPU to GPU. That's always going to cost time. But as you start getting bigger and bigger, when you start getting to real problem sizes, that's where the scaling hits. And in this case, that great result up there was with 8 GPUs, but anywhere between 1 to 8, you see the scale, the performance increase as you go, which is, you know, what the graph showed.
Yeah, and just as a stress test, right before this talk, we ran a 160K Metmol in the same 8 H200 GPUs, DGX, and VL that we showed you this. So we can reach somewhat big matrices or bigger matrices than you could in 1, 2, or 4 GPUs. So yeah, this is the overarching results.
And yeah, this stuff we can skip. It's just future work with the multi-stream work that we're doing as part of the Google Summer of Code project. So I think we can close out here and take questions. Thank you.
That's nice. Bye. Let's thank our speakers. Unfortunately, we really don't have time for a question. So let's get the next group to come up.
We're hanging around the conference. If you guys have a question, just stop us, and we obviously like to talk a lot.
Yeah, thank you. So our next talk is going to be from Guillaume, Mikhail, and Simeon. If are you the only one giving the talk? Okay, then do you want to just use the hand mic and make your life easier?
Okay. Hi, everyone. So I'm going to talk about work that we've been pursuing with a colleague in the US, Michael, and with my brand new PhD student, Simeon, on hardware agnostic linear programming on the GPU. And first, I'm going to motivate that. And if you want to follow along with the slides, you can check them out here, knowing that I'm going to show benchmarks on GPUs. And if you click that link, the benchmarks are going to be run on GitHub Actions on CPUs, which is why they're noticeably less convincing. So as motivation, since I'm French, I'm going to ask you to imagine you're in a country where the bread is good, and so you're actually going to a bakery, and that bakery, they can produce two kinds of items, right? A croissant or pain au chocolat. And if you don't know, the pain au chocolat is sort of more fancy version with chocolate in it. And for each of these, let's simplify and say that they need three ingredients besides the chocolate, which is butter, sugar, and flour. And these ingredients are in various proportions depending on the product that you want to come up with. And of course, these ingredients, they have to come from somewhere, so they have a cost per kilogram each, and they also have maybe a maximum supply, for instance, due to the size of the fridge in which you store your butter or whatever deliveries you can arrange for a given day. And so the question, if you're the French baker, is how much of each item should you manufacture in order to maximize your profits? And if you're not familiar with optimization, it might take you a little while to see, but this is actually fairly standard. It's an optimization problem. And an optimization problem, it's composed of three things: variable, constraints, and an objective function. So here we go. What are our decision variables, the levers that we can pull? They're, on the one hand, they're the quantities of pain au chocolat and croissant that we want to manufacture, which I'll denote by C and P. And on the other hand, we also want to compute the weights of butter, sugar, and flour that we're going to buy from our suppliers. Our objective in this has two parts. On the one hand, there's going to be the revenue that we get from selling our stuff to the hungry French people and the tourists who are sick of German bread. And the other part of the objective is the cost which we pay to acquire our ingredients. And finally, we have some constraints. We have the maximum supply of each ingredient, and we have the fact that we need the proper quantities of each butter, flour, or sugar to make the stuff that we're going to eat. And so if you look at what it ends up looking like, it's on the right. It's a maximization problem over 5 variables where you have an objective that is linear in all the variables, which is the revenue. You have some constraints related to maximum supply here on the butter, sugar, and flour, and you also want to manufacture a positive amount of each product. And finally, you have the constraints saying that for the quantity of butter that you're taking in grams, there's going to be 35 times your number of croissants plus 25 times the number of pain au chocolat. All of this to say, this, as so many other things in life, is a linear program. A linear program is an optimization problem where you optimize a linear objective subject to affine constraints. And so you can typically write it as follows: minimize or maximize C transpose X, where X is a vector and C is a cost, subject to AX smaller than B, where A is the constraint matrix, and B is usually called the right-hand side, although you can write it on the left, and I don't mind. This sounds relatively simple, but it's sort of the bedrock for modern optimization as we know it. In particular, it's useful also for nonlinear convex problems as a subroutine of Frank-Wolf. It's useful for combinatorial or integer problems as a subroutine of branch and bound. So it's essentially popping up everywhere. And we want to parallelize it. First of all, because we can. We have GPUs. We bought them, or they're just sitting somewhere. We want to use them, in particular when the instances that we have to solve get pretty large. Think millions, even billions of variables or constraints. Or an alternative option would be to solve several instances at once. Of course, there are also good reasons not to parallelize, because the current best solvers for linear programming are called the simplex and interior point methods, and they're very, very sequential. They require sparse linear algebra, especially computing and keeping updated matrix factorizations. So this is a very sequential sort of code with a lot of indexing and control flow. And in addition to that, we usually want high precision, like at least 64 bits of precision, which is not very GPU friendly. So just to give you an idea of what these algorithms look like, my co-author Michael has developed this really nice website called LPviz. So you can define the sort of geometric area where your problem will live. This is what we call a polytope. And then you can create an objective vector and you can see the behavior of the various algorithms that I'm talking about. So 5 minutes left or 5 minutes? Okay, thanks. So the simplex algorithm is a rather simple one. It goes to the boundary of the polytope and then finds the first vertex and then sort of hops from one vertex to the next until it finds the vertex that is most aligned with the direction of the objective. The interior point method, as its name suggests, it sort of walks through the interior of the polytope, starting from the center towards a vertex. And I'm going to tell you about another method, which is the primal dual hybrid gradient, which is essentially doing this kind of funky spiraling thing. And for some reason, this, although it does sound kind of weird, is actually the best thing you can possibly hope for on a GPU. So let's get to it. As I said, there's good reasons not to parallelize the solvers we have. So that doesn't mean we should not parallelize at all. It just means we should change the solver. And the main, I would say, one of the main advances of recent years in operations research is people actually coming up with an idea that is basically the same as in deep learning, which is that you only need gradients. And if you only need gradients, what you end up with is called a first order optimization method. And it's really nice because you can forget all about these factorizations which are bothering you, because factorizations and linear systems, they're a feature of second order optimization algorithms. And when you do first order, the only thing you really need to do is matrix vector products. In this case, the constraint matrix is the one we're interested in. And in a typical optimization problem, not the small bakery that I told you about, but actual large scale optimization problem, not every variable appears in every constraint, and not every constraint has every variable in it. So that means the matrix is very sparse. It has mostly zeros. So the core primitive of these primal dual or first order algorithms is a sparse matrix vector product. Oh, oh, right. 3 minutes left. It's an amazing algorithm, and the proof of concept was made in Julia, actually, for the first time. So we designed a package that does it essentially the same as everyone else, but so much better. I don't have so much time to go into the details, so I'll leave you to admire the table in the package README. I just want to point out that it is, of course, hardware agnostic, because that's how we do things here. We coded it with kernel abstraction so that it runs on your laptop as well as on any cluster that you might have. It's type generic, which is really important if you want to use some fancy sparse matrix structures that you design for your specific problem, and that's sort of the main additional input that we do here. And it's also batchable, so if you have several problems, instead of one, you can solve them all in lockstep, in which case you're not using a sparse matrix vector, but a sparse matrix product. I wanted to do a package demo. You won't get the package demo. Just know that you can use the package. It works, it runs, and it's even interfaced with Jump, which is perhaps the most interesting part. So if you're used to the Jump package for solving optimization problems, this is just another solver that you can plug into Jump. As a conclusion, we have more functionalities coming up because Simeon is going to keep working on it, and so will I. Pre-solving, polishing, infeasibility detection, etc. I'm very excited about fighting my way through reactant integration as well, and extending it to nonlinear problems as soon as I get batching working in differentiation interface. You heard it here first. That's all for me, and I'll take questions if there's time for questions. Yeah, I'll repeat it. So theoretically, since we're basically coding it in a sort of hardware agnostic fashion, if you have a matrix vector or matrix multiplication that runs on multi-GPU setups, you can just plug it in. It will work. It works on your CPU. It works on anything. It's just we come up with a few sort of default kernels in case you don't have this stuff to back it up, but you can definitely try it. And as a side note, if you're looking into optimization for Dagger scheduling specifically, I think you're more in the combinatorial or integer programming setup that I mentioned at first, in which case this is not exactly what you want, but there's been recent progress on using this as a subroutine in integer programming solvers. So we definitely have a chat about that. Any other questions? See, that's your fault, Katie. You made me stop 5 minutes too early. Yeah. Yes, and right now, as a result, it's like we have not spent any time on optimization. The batching functionality was actually merged like yesterday. So right now it runs, but we haven't spent much time sort of squeezing performance out of it or fusing kernels or whatever. So it runs because it's essentially coded as a GPU arrays reliant package. So it's vectorized operations and linear algebra. So it works wherever you want to use it. And until recently, actually, this whole family of packages, cuPDLP, it's the family of packages that first demonstrated that this algorithm could actually scale to GPUs. And the initial prototype was cuPDLP.jl. So they actually used Julia to demonstrate it, the Google team back then. And the AMD version until recently didn't exist because, as you can guess, CU stands for CUDA. So the AMD edition here is kind of new. So the only really agnostic alternative that you have is this MPAX package in Python, but you cannot plug any sparse matrix into it, and you're also rather restricted in terms of the floating point types that you can use in there. Julian. No, I would say it's bad, honestly. So I spend the whole morning looking for one instance where the GPU version actually speeds things up because I don't have a CUDA laptop. I have a Metal laptop, which is noticeably slower. So it doesn't have any built-in sparse GPU linear algebra. But I did find one instance. So this is actually the largest instance of the MIPLib dataset, which is a famous optimization dataset. So I picked the one with the most constraints. As you can see, it has something like 3 million constraints. So this is starting to get rather big even for CPU, and it has almost a billion non-zeros. And you can solve it on the CPU. What you do is you can simply set up your algorithm saying, I want to solve it in float 32 with in 32 indices and the sparse matrix CSC default format. And you put in some tolerance and time limits. And you converge in like 12 seconds for the very, very lax tolerance that I put in. And if you want to move to the GPU, all you have to do is change a few things. You keep these same floating point and integer formats, but you give matrix formats that you want to use. So if you're on CUDA, this could be cuSparse matrix CSR, for instance. So this could be some multi-GPU matrix format. And then you specify the backend you're working on, like Metal, AMD, whatever suits you. So this is Metal in this case, and you see that we converge about 2 times faster. So right now, again, this is a very, very unoptimized version of the package, and the larger your instance is, the more speedups you will have, but don't expect too big of a speed up, especially like on Metal or on JL arrays, especially if you run it in CI. But as now that we have the basic infrastructure and sort of design locked down, what we're going to do is we're going to try to optimize each individual component and benchmark more properly against these Python and C alternatives. Yes? So the question is, how does sparse linear algebra on GPU work? The answer is it's a bit complicated, especially because unlike dense linear algebra, you cannot always predict where you're going to pull your data from. So there's this indexing operation which is really crucial, and so there's been hundreds of research papers on exactly what the right matrix format is for matrix vector multiplications on the GPU. The answer taken by most of these other packages is cuSparse CSR. So that's sort of what the majority of these are going with. And the real answer is it depends. It really depends on your problem. Like we're working with Zimeon on an application to graphs in which you have as a constraint matrix the incidence matrix of a graph, which has 2 non-zeros per row. And for that specific format, you can do much better than CSR. And in general, for any given problem, you can come up usually with something that is smarter than CSR. So Our approach in typical Julia fashion is to say, we're not going to prescribe what you can do. We're going to code something that is generic enough for you to plug whatever you want into it. And if you find something that does the better sparse matrix vector product that you need for your application, feel free to plug it in. And let's say with 95 to 96% chances, it will run. Goodbye.
Okay, I'm going to present my PhD work on about Julia and FPGA. To start, computation needs are growing rapidly, notably because of simulation or machine learning, for instance. And in this case, general purpose CPUs face fundamental limitation. So hardware accelerators have been introduced, such as the GPU, TPUs, or even ASIC. Each one of these hardware accelerators provide a trade-off between specialization and performance. And one of them, so the FPGA, which is a class of configurable secrets, enables to explore this trade-off by using different design. And one important information is that all these hardware accelerators need specific software to work. So to introduce this, I want to talk about a bit about formal languages. So it is a construction to modelize abstraction. So with a syntax which gives the structure of the representation and semantics which gives the meaning. So there is several different kind of formal languages, so general purpose programming language, such as Julia, for instance, domain-specific language, for instance, CMake, descriptions such as Verilog to describe the hardware, or even intermediate representation, which are used by compilers. So here, I want to talk about Julia, a bit about Verilog, and mostly about the interpreted presentation, so Julia IR code and AMAL. So I want to use an example. So here it's for representation of Fibonacci in 4 different languages. So a mathematical representation, a representation in Julia with interesting abstractions of such as function, variable types, or control flow expression. Another programming language, so the assembler, which is a lower abstraction level than Julia, for instance, and which is bound to a specific computation model linked with CPU. And we have a similar languages for FPGAs with the hardware description language. And this language are used to generate the FPGA configuration. And in this representation, we use the register transfer level model. So we have a sequential and combinational logic. So we can we can represent synchrone circuits. Okay, so now we see we have different level of abstraction. Everyone represents some kind of similar piece of information, and can we translate one language to another? And yes, so with a compiler. And the use of the compiler is to enable to automatically handle the abstraction gap between two abstract um, two different abstraction between two formal languages. For instance, we can have software compilers which from a programming language enables to get some kind of assembler, or an hardware compiler which from for instance, a similar programming language enables to get hardware description languages. And that kind of hardware compilers is named high-level synthesis. So now I want to focus a bit more on the software part, so with Julia. So the Julia compiler is composed of three parts: front end, so with the classical element we have in a compiler, so a parser, a first intermediate representation with an abstract syntax tree, and what Julia used is another intermediate representation, so which is used to in the middle end to do the type inference, and after this to be used by an optimizer. Then we got a new intermediate representation which can be used by a backend. So here it's a LLVM backend, and so after this backend we can get the CPU assembler. So what we can see with Julia is that this is there are we can use modular targets. So for instance, using a custom backend, we can, for instance, target GPU. Or for instance, if we transform the middle end, we can target XLA and so TPU. And so the idea here is to see hardware design and high-level synthesis as a custom target, like the other. And there is several works around this, using several different approaches and different high-level synthesis framework. But there is a common intermediate representation. It's Julia. So no, not Julia. Sorry, Emalaya. So I want to focus a bit on Emalaya and the use of this framework for heterogeneous compilation. Okay, so Himalaya is a compiler framework which enables to build modular compilation toolchain with different level of abstraction. This is done using some kind of namespace which are dialects, which defines operation types and concept and transformation on them. We can see some classical dialects, so the standard dialects. On the right, we can see a definition of general matrix multiplication using this dialect. And what is interesting with these dialects is that we can manage semantics of different level of abstraction and so enable a different level of optimization. And for instance, we can give two use of dialect for hardware design. For instance, software dialect are used by Scala HLS to do design space exploration, um, or the circuit project define Verilog. Okay, so now I want to focus on Himalaya front-ends. So there is two main approaches, a static one and a dynamic one. So I will start with the static one. So the ID is based on the Polygeist front end. So Polygeist is C2 Himalaya standard dialect compiler. In Julia, we have Brutus. The idea behind Brutus was to create a different backend optimizer for Julia. And several works has been done following Brutus ID. So two targeting FPGA and one targeting LinArg direct. So all these static methods work. So the idea is to create some kind of higher level intersect instead of using the classic Julia one, which can be fit to LLVM operation. Here we target a higher level, so exploiting a Julia abstraction. So for instance, here with the generic method, we can match them to Himalaya operation or match Julia type to Himalaya type. And there are cases where we got some kind of semantics gap. For instance, 1 or 0 based indexing. So the idea here is to introduce Himalaya abstraction into Julia to support this new types and new semantics. So and the idea behind this is just to modify so the middle end with custom typing and a custom optimizer. This approach has several limitations because it translates one language to another one. All the dynamic construction cannot be supported, such as union or any. And there is some problems too linked with the abstract interpretation because we can lose some kind of precision on the types. So another approach is the tracing. So the idea behind this is not match a compiler representation to a dialect. Okay, so the tracing. So the tracing is a kind of symbolic execution. So the idea is to execute a program and get some metadata, which can be used for logging, instrumentation, or cogen. And what is interesting here is MLIR cogen. So JAX is a Python tracing system for so the XLA infrastructure, and which use a high-level dialect based on stable HLO. So in this dialect, we got linear algebra, neural network, or control flow operation. And this dialect has a semantic of tensor and non-mutable operation. So it's some kind of functional dialect. And Recton is a tracing system inspired by JAX, and it adds a stable to stable HLO optimizer. So how is this tracing working? So the idea is to use the multiple dispatch and using the type system of Julia with the uh, traced parametric type here. So the idea is one we got like we can see on the function call stack um, when we have a traced int, for instance, we don't execute the computation, but we create a part of a malware program. And with this, we can get the program here. But this approach has several limitations. The biggest one is that only one trace can be executed, so we cannot handle branches, so we cannot support if or loop. So yeah, so the two approach have several trade-off, and so the solution is a third approach with an hybrid, which add to the tracing system a part of static analysis to detect and transform the branches to get a sound tracing. So with this approach, we can trace all the polybench reference benchmark. Okay, so now we have Julia Amalaya modular and powerful front end. So now let's focus on the backend. So we got circuit. So the idea behind circuit is to see that hardware design is hierarchical. So define different level of abstraction of hardware dialects. So in this, we got hardware.gl, which is a first initiative to use Julia with Circuit, so using a static front end. So now what I propose is a new toolchain using Recton and using a different target, which is a circuit core dialect. So the idea behind this is to use to have several use cases. So the first one is the simulation with the oscillator simulator. A second one is to do resource estimation using RTL synthesis. And a third one is to apply the other methodologies for instance, fault mitigation for instance, a register triplication. And so I just give a really simple kernel for this. So it's a square kernel with a broadcast, and here we got the stable HLO interpreted representation. From this, we can get the Calyx, so the HLS framework representation in from following the pipeline. Next, we can get the same interpreted representation, but after the synthesis. So it's similar to RTL level of abstraction, and from this this representation can be transformed to the core dialect and be used after. So just to conclude, so the idea here is to take advantages of the expressivity of the compiler of Recton, and the other side use so the circuit RTL dialect to explore a large scope of usage. And so this is an ongoing effort. For now, there is trouble dealing with the lowering part between enzyme JAX and calyx, because calyx has some kind of hard limitation of the kind of control flow graph it can support. And that's all. Sorry? Okay. Yeah. Yeah. So the question is about using Julia to control FPGA. Yes, I think it's really interesting. So I don't have the time during my PhD to to go this way. But yes, what can be really interesting is to do some kind of instrumentation, so directly on the FPGA, so it can enable some kind of hybrid methodology to explore design and control by Julia. So the question is about dynamic scheduling, if I understand correctly. Yeah, there is a lot of FPGAs and more high-level synthesis framework which achieve dynamic scheduling. So with a lot of data flow. So I talk a bit about dynamic, but recently there is a large effort to introduce some kind of hybrid scheduling. So to get the advantages of static scheduling and the modularity of dynamic scheduling. So for instance, with I don't remember the framework, but yeah, it's a framework which use Himalaya. So it can probably be supported with Julia. So here I'm focused on circuit because that was the choice of AdWeb.gl, but there was lots of HLS frameworks which can be explored um, using Himalaya. Yeah, the benefit here is to do some kind of design space exploration. For instance, here with Reacton, for instance, we can define neural network and using enzyme to get the differentiation. And for instance, we could try a different design of neural network and get an hardware design from it directly. For instance, to do this with VTS HLS is probably a lot of trouble because with the C++ there, we get some kind of only templates and stuff like this, and it's very limited to that kind of large scope exploration. I don't know too much about reprogrammation of FPGA on the fly, but yeah, that enable, in addition to what I talked about instrumentation, a large scope of methodology. What is probably missing is some ways to lower efficiently information in all the pipeline, but it's probably not a reactant problem, but an MLIR problem. Um, but except this, yeah, this front end is already much more developed than the static approach developed before. Yeah. Okay. So the question is about circuit and problems and I don't know to call that. Yeah, the problem here is that so all the RTL part of the circuit is well developed. It's working nicely. For instance, I talk about fault mitigation, so it's really easy to do that kind of stuff with it, or to do simulation. But the high level statistics part is really lacking. For instance, the integration with the Calix framework has a large scope of bugs, and for instance, there is a difference between the semantic of the Calix dialect and the Calix intermediate representation from the Calix compiler. So it's it's a lot of work to match them, because the compiler exists, the dialect exists, but I suppose no one has tried too much to merge them. So yeah, there is a lot of bugs, and it can be really hard to debug because hardware design interpreted representation can be very large and
Um, Okay, here we go. Something's happening. So the next speakers are me and just of us. Really, really exciting. So we're going to be talking about GPU acceleration in the quantum GitHub ecosystem, and I think we're ready to go. So we're going to start really quickly introducing a tensor network, which Lucas is much better at doing than me. So here you go.
Oh, now you're stressing me out. So in order to talk a bit about tensor networks, for those people that don't know, let's start maybe with tensors and just like start from the basics. And what I don't want to do is start with a tensor is something that transforms like a tensor, because I feel like that's not the most useful way of introducing this. And I think for like a computer science background, people actually we tend to think of tensors as just pick a basis and fill everything with coefficients. So this is really just a multidimensional array. And like for the purposes of this talk, we can think about it in that way the best. And so then it's just like a term we use for array Tn in Julia language. And so, like, why do we care? What's the point? Well, a tensor can represent a variety of things, and one thing is basically just saying that any function of a set of discrete variables can be represented as a tensor. And in that sense, it's not a very smart representation. You just take a big blob of memory, you fill it with every single entry that this discrete function can take, and this is now your tensor. And the reason that we in particular care about this is that one such function that you could think of is actually a quantum wave function, which has this exact same property, where you encode all of the amplitudes of the different basis states in the quantum system as a tensor. There's other things that fit in the same formalism, and actually like quantum circuits are very easily represented like this as well. And so you can see on the bottom there, like if I take a quantum circuit that's built up of a bunch of gates and I have some qubits, then again, I get a wave function out. So now I have a tensor. One of the things that you might have seen in the quantum circuit is that, well, there's some notation that comes along with the field. At some point, like we've reached peak intelligence and the math was too hard for us. So we went back to just making small drawings. And actually, like none of these drawings are super complicated in the sense that the top thing is just saying like every single tensor we have, we will represent as a shape, a blob, in this case, circles. And for every index, for every dimension of this tensor, we will draw a line. And then anytime we connect lines, all we mean is just sum over the joint, the joint indices. So the top one is just matrix vector multiplication. The reason why we do this is that you can quickly see that the examples on the bottom gets harder to just parse the math part. You get a lot of indices floating around. And actually, if you really like get down into it, you run out of alphabet, which is a bit annoying. And so we can kind of test this in the sense that maybe we'll take some questions or some answers from the audience. And so, like, does anyone want to tell me what the top figure would represent? You are free to shout it out, not all at the same time. Thank you, a dot product. The second one being a matrix trace. Let's go. And then the final one. Yeah, like this was a trick question. I don't actually have a lot of words for this. It's just a tensor contraction. All right. So like that's kind of the entire point about tensors. But I was promising tensor networks, and so maybe like to start out by a little bit of motivation is like, okay, why do we really want tensor networks, or maybe even why do you choose, or how do you choose a representation for your data? And I think one of the properties you tend to want to have for a representation of data is that you want it to be, well, efficient in the sense that it's compressed as much as possible. And one of the annoying parts about tensors is that as you start increasing the number of indices, as you start to add more of these legs to these shapes, actually the storage requirements of these things like grow exponentially. And we don't really like to work with exponential number of parameters. And so if we, I mean, this is a classic quantum problem, but I mean, it shows up in various high dimensional data things where you just, I need to store an exponential number of coefficients. How can I compress this? And tensor networks follow from the idea that, well, if I look at a matrix, I can compress it, like depending on what the structure of the matrix is, by taking an SVD and making a low rank approximation of this matrix. And by doing this, like very often, if you have some data that is structured in at least a little bit of a way, you can actually get away with throwing out a lot of the singular values without losing any of the data. And so if you think about like this SVD-based factorization as cutting a matrix, which you can see on the bottom left, into two pieces where you reabsorb the singular values on both sides. This is a compressing algorithm, and you can actually just, take the scissors, put them between each of the parts there, and factorize this entire tensor into components. And at the end, you end up with a polynomial amount of data necessary to store this. And so the linear form where you just, like got everything along a line is the matrix product state formalism, the one here in the middle, which has the most, let's say, supporting theory and is the de facto standard for one-dimensional quantum, for tackling one-dimensional quantum problems. But there's a variety of additional things that people have been working on, in the sense that you can do 2D square grids, you can do 3D things, you can do things that are in between. And even like something that is often kind of forgotten is that you can also do thermodynamic quantities, in the sense that I can actually tile the entire 2D infinite grid this way, or 1D infinite chain this way, and most of the algorithms still survive.
So we, for a variety of reasons, want to be able to simulate these objects on the GPU. And the perhaps surprising thing is that we don't need that many operations to do so successfully. Another way of saying this is that you can get a whole PhD in physics doing like 4 linear algebra operations, which is pretty sick. So we have, as we mentioned earlier, contraction, where you can have like some arbitrary ranked tensors here, where I've drawn them with beautiful orange legs. And then as soon as we join together the legs, we do an Einstein summation over the joined ones, modulo some complex stuff we'll discuss in a second, and then we end up with an output tensor C. This is very similar to like a batch gem operation for anybody who's done something like that. We also want to do the QR decomposition, where we end up decomposing A into 2 matrices, Q and R. Q is left unitary, and R is upper triangular. I'm assuming many people in the GPU Mini know basic linear algebra, but just in case, it's after lunch. As mentioned, also, if we need to reduce the size of our tensors, we can use the SVD, which again I've shown in a cartoonish format here. And the other one that we occasionally use somewhat frequently is addition, where I've also sort of cheated here. You can see that A has 2 legs on the right and B has 2 legs on the left. So we might occasionally need to permute one of our tensors, or do effectively like an in-place permutation operation to end up with the output that we want. So if we can implement these 3 or 4 things, you can simulate some pretty complicated physics to like very large number of sites. Like Zoe and Co were mentioning this morning, these tensor network algorithms are basically the standard in 1D. So you can do like many thousands of quantum particle simulations with this. And I just want to mention that although we've drawn this in kind of a cartoonish fashion, there's actually a lot of complicated math going on here. So I'm not going to read all of this text, and it might also be a little blurry in the back, for which I apologize. But if you really want to give yourself a migraine, you can study all of the wonderful category theory that underlies a lot of this at the tensorkit.jl documentation. If you can understand what this paragraph is saying, you may want to speak to a doctor. But all that's to say is that although these like sort of cartoon diagrams look relatively simple, translating them into something we can actually run on the GPU is not always so easy. And again, here's sort of a more complicated schematic of what a relatively simple tensor contraction can end up looking like once you have to start taking into account the various symmetries and rules about the way you have to work with the indices. Okay, so we have this really great suite of packages at the so-called Quantum GitHub that we have a really cool cartoon for. So I don't know if you want to summarize what each of these are.
Logo patent pending. Yeah, so I think, I mean, it looks a little funny, but there's actually way more going on behind the scenes, and we thought about this quite a lot. And so the idea here is that there is the brain of the octopus, which is holding on to all of the low-level things. And so one of the low-level things, which is in the center of the brain here, is tensor operations, which you might have heard of. It has been around for quite a long time, which is just doing tensor contraction and einsum summation notation things. And then, I mean, the thing we then like started building on top of this is TensorKit, which you can see all the way at the top. That one is the one where we try to hide all of the migraine-inducing category theory from anyone. But you can also like just dive deep into that one if you really feel like it. And then finally, or more recently, as Katie said, the two main operations we have are basically, well, contracting things together, also known as take many tensors, make one. And then the opposite, factorizing tensors into many tensors. So take one tensor, make many. And this is matrix algebra kit, which is where we tried to put some of these things as it's maybe a bit of an alternative to linear algebra that we needed. And then once you have the brain, or well, whatever an octopus usually has, I actually don't really a brain, great. We attach to each of the legs the higher level packages that implement the tensor network algorithms in 1D, 2D, or even everything in between for the bottom TNR kit. And the separation is kind of important in the sense that you really don't want to be dealing with the complexity of this entire stack at every point. I mean, this is good programming practice that we all know. You want to keep things modular, keep things separated. And in particular here, like one of the things that is really important is that our tensors really want to be basically anything that looks more or less like an array. And so, okay, the dense version is the standard one where you all start out with, but one of the other things you want is like, oh, I want to be able to put a coup array in there. I want to be able to put a rock array in there. And then finally also like various kinds of sparsity, various kinds of block sparsity, and anything else you can come up with that might be a useful representation in the context of this category theory has to fit in there and cannot seep or leak its way to the higher level packages. So yeah, I think, I mean, we did a lot of work on this and tried this. And so the entire premise is if TensorMap has good support for GPU, then all the other packages don't have to worry about this. This turned out to be a very small if, and everything, of course, worked out of the box, except for maybe some other here and there wrinkle that Katie can tell you more about.
Yeah, so one big goal that we've sort of been pursuing when we're trying to have a tensor map type that can take all these kinds of arrays is that we don't want to have to write very specialized code for each specific array type or each specific block sparse pattern or something like that. And one big advantage of the Julia GPU ecosystem, as anybody who used GPU arrays and kernel abstractions knows, is that you can more or less have a write once, run anywhere for a lot of the functionality we need. And then you can spend the rest of your days, as I do, walking blindfolded through a barn, stepping on rakes, because there's no wrapper for like diagonal times a regular coup array. So a lot of what we've been working on has been adding higher level functionality for GPU-based linear algebra and things like that. And then the occasional very GPU-specific handling of factorizations like randomized SVD, where there's a really big performance advantage to doing that. And another big motivation for us to do this is that the current state of the art, especially for some of the simulations we're really interested in doing, really requires the GPU to be competitive. So this is just an example, and I've included the archive reference at the bottom, of a relatively recent paper from the group at the University of Amsterdam, where they're using some sort of QR-based decomposition to do a really large-scale 2D tensor network simulation of a quantum physical system. And this is actually a good example also of how we're having, as a community, to adapt our simulations to running on the GPU, because as many folks probably know, even with randomized SVD, you don't get a huge amount of benefit from performing SVD on the GPU. There's a variety of reasons for that, but QRD composition, there tends to be a somewhat better acceleration, and for this reason, they're able to do a very, very large simulation pretty efficiently and with quite high accuracy on a two-dimensional tensor network. So in short, if we want to be able to compete with sort of the cutting edge of what people are doing, we really need GPU support in our libraries. And of course, as we also probably know as GPU developers, it's really not as easy as just like saying GPU equals true, and then you, I don't know, go on vacation for 3 weeks, and you come back and your simulation is done. One problem that we encounter very frequently is that the tensors we want to optimize can be very, very large, by which we mean like they can be many hundreds of gigabytes. So even if you buy the most expensive GPU on the market, it doesn't have a whole terabyte of onboard RAM. This then necessitates doing all of the multi-GPU stuff that other people in this mini have been discussing. As we mentioned, these tensors can have really complicated sparse structure, so they can be block sparse, and even worse, they're not necessarily block diagonal. So that, for example, already precludes you from benefiting from the inbuilt cuSparse block format, and it means we have to write a bunch of custom logic and then test it on all of the GPU backends we support. Also, because we're really stubborn and perverse people, we want double precision complex numbers, and none of the GPU vendors want to support that. They don't like it. They don't want to hear about it. So that also can be something that can affect the accuracy of our simulations, where it's really important for us to be able to resolve, for example, differences in energy that are like very fine, even in the double precision context. And then finally, of course, you know, whenever you see like a marketing material for one of these cars, they show you the gem benchmark, and you're like, wow, that looks really good. Like they're doing like 12 terabytes a second of gem. And that's what the GPU is designed to be really good at. But the second you move away from that, the story can become a little bit more complicated. And indeed, for us, a lot of the operations we need to do are not as efficient as GEM. So there's a lot of work we're doing on improving the support for sort of the very specialized kernels that we need on the device. Okay. So we're going to talk, I guess, also really quickly sort of about the state of the art and try and finish with enough time for questions. So we'll see if we manage. So we're currently supporting both CUDA and ROCm, and Lucas is also working hard to add support for Metal for all of you Apple users out there. If anybody here is running tensor networks on Apple hardware, please come see us, because that's crazy. Also, our users have access to both of these. For example, we have folks running on Lumi, which is an AMD-based system, and then also Mare Nostrum at Barcelona that is CUDA-based. The support for what we need from AMD and NVIDIA is not always equivalent. Again, probably not too surprising. And so we're doing a lot of the kernel writing we need to do with kernel abstractions, which is actually very helpful. And then we also have this problem, and if you want to know more about this, you should really talk to Lucas, because this is what his PhD thesis is about. We have the nice feature that many of the physical models we want to simulate have some sort of symmetry, either local or global. This is exactly what induces the block sparsity in our tensors, but it also makes it that we have to do a huge amount of accounting and bookkeeping to avoid losing track of the blocks, and writing efficient code that handles block sparsity well is very hard. And one thing that is kind of nice for us is that cuTensor now has a library that supports this, and we're working on integrating with it. As far as I know, HipTensor does it, and also we don't really integrate with HipTensor at all. So that's a to-do. So right now, we're sort of in the situation where we have tensors. Basic operations are basically completely supported on the GPU. If you find one that isn't, please open an issue. And from that, as we mentioned earlier, we're able to build up a lot of the higher level algorithms that we want to run. Things on like these one-dimensional objects, MPS, MPO, the two-dimensional PEPs, including things like sort of, I guess, one of the more standard algorithms, CTMRG, as well as belief propagation. We're working on setting up support for automatic differentiation. If you're interested in that, come see our talk tomorrow morning in the computational models mini. And as also probably many of us know, Autodiff plus GPU is always really fun, and you really feel good about yourself when you're doing it. And the next thing that we are really going to start working on is, now that we have basic support, we need to benchmark and profile. So we're also working on this. And as we mentioned, we also are going to need to move to this distributed GPU-based simulation soon. Even a single tensor that we want to simulate can be extremely large, so it's not going to fit on a single device. And we can even use this to take advantage of the block sparse nature of our tensors. We're evaluating various options for this, so hopefully we can maybe get some inspiration during the mini, or possibly already did. And again, if you're interested in specifically the GPU plus AD aspect of this, come see our talk tomorrow morning. And I think that's basically everything. Also, we have two of our colleagues presenting at the poster session, so please come see their posters if you want to learn more about tensor networks and how interesting and weird they are. Thanks, everybody. Okay, so we have like 10 minutes for questions, I guess, so perfect. Felipe?
It's a QR factorization over a tensor, as in it's not a batched QR, if that is the question. So if you can provide me with a QR decomposition for tensors that don't fit on one GPU, we should talk. Yes, we should definitely talk, because that's kind of the limit of where we're pushing things. Basically, memory bottlenecked by how much things fit on one GPU. Anything that works, I'll take, or will take, I guess.
Oh, okay. Sorry, who? So the question was, are we seeing any benefit from using these vendor-specific libraries like cuTensor? So I think for just my experience is, I mean, if you've used cuTensor, you can see like when they ship you the .so file, it's like 500 megabytes. It's really big. It's like almost as big as cuBLAS, I think. And it's partly because they have many. Okay, I don't work for NVIDIA, so this is speculation, just to be clear. But they have quite a few sort of like hand-rolled specialized kernels for some of this, where they do something perhaps more sophisticated than like permute, BLAS, permute, which is, I guess, the more naive way to do this. But for things that are like relatively square and you have the index layout is pretty good, it's very hard to beat batch gem, right? And even for things that aren't that square or like don't have a super friendly index layout, batch gem is like really, really good. So I think, okay, this is like a very bad technical way to describe this, but like, for example, if your tensor is like hot dog shaped, um, and you have like another tensor that is by which I mean it's like much longer in one index than the other. Sorry, I did not sleep a lot last night. That can be for like, and you have to do a bunch of permutations. That can be a situation where there's like some benefit to using cuTensor, but otherwise the batch gem is like, yeah, it's very, very good.
I mean, to add to that and come back to the exact same points, if you need to permute, gem, permute, you need 2 additional copies of your input data. And so that basically means that I need 2 additional GPUs, which, expensive.
Does anybody who's not Felipe have a question? Sorry.
Let me retake the questions. So the question is like for these algorithms and these quantum things, is the linear algebra thing we need SVD and always SVD, or can we get away with other types of factorizations, such as, for example, a Schur decomposition? Do you want to take this? Or
I mean, yeah. So, for example, the reason people in this field are like very married to SVD is if we go back to like this MPS representation, part of the reason it became and is the gold standard in one dimension is that with the SVD or even the QR, you end up with in the situation where if you factorize one of these tensors, you end up with this matrix U that's left unitary and this matrix V dagger that's right unitary. And then you also have some information in the singular values that effectively allows you, like when you truncate the SVD, you know exactly how much information you're losing about, like how much effectively like entanglement between the two adjacent tensors you're throwing away when you do that. So if you do a QR, you will again retrieve this unitarity property, but you no longer truncate, so you don't throw any information away. Um, and the reason this left and right unitary property is really, really helpful is it means you can operate exactly on like 1 or 2 tensors at a time without having to consider the entire network. For the 2D tensor network, for a variety of reasons, that's basically not possible to do, which makes it much, much harder to simulate, which is also why like this is kind of the research frontier, I guess. And it also, the left and right unitary feature means that when you optimize this, you only have to solve a regular eigenvalue problem, not a generalized eigenvalue problem, which would, I mean, yeah, it's not great to have to solve a generalized eigenvalue problem. So if you have like another decomposition you like better that can give me those 2 properties and is easier on the GPU, then yeah, that would also be great. But yeah. Yeah, so that's the reason, kind of like for better or worse, we're sort of joined at the hip with SVD and QR, and our beloved LQ factorization as well. But if anybody here is a numerical linear algebra person and wants to invent something better than SVD, please talk to us. Oh yeah, but then you also lose a lot of stuff. Yeah, it's very annoying.
Like in these factorizations, the layout for the memory can be trapezoidal, which is beneficial for performance. I can not answer this question because I don't know about any of this.
I think the short answer is we haven't really looked into it. It's the sort of thing like if we need it, we'll cross that bridge when we get there. But for now, we're still so hampered by like SVD and then just like, like give me the piece of the matrix, put it back. Give me the piece of the matrix, put it back. That like we aren't even sophisticated enough to think about that. Also, so thanks for your attention. And if the next speaker is here, Emmanuel, if you want to come set up. Thanks everybody.
Thanks. So, pure Julia with and we want fast, flexible, and portable Julia primitives that are so fast. So this is a kernel forge package, and I'm going to tell you how it works, or hope to have the time to tell you how it works. So there are mainly three things. So I'm omitting many things, but there are mainly three things you want from a GPU library. Basically, you want it fast, you want it flexible, and you want it portable across other architecture. And so there are already many existing GPU libraries, starting from kublas and kub. So they are very efficient, and basically it's very hard to beat. Like you cannot, very hard to beat kublas and kub. But the problem is that they are usually not flexible because they are compiled for specific types like float 32, float 64. So you unlimited to operators like plus and times. And they are specific to vendors like NVIDIA or AMD. So there are C++ cross-architecture packages like Cocos, Rajas, and other friends. They are very fast, though a bit below vendor, so I measured it. And flexible there means that you have to write your own functor by hand, which can be very messy. And okay, so it's supposed to be portable if you take the time to compile for the right architecture. And in the Julia landscape, there is CUDA.jl, so the most known for NVIDIA, and accelerated kernels that provides that is really flexible, pretty fast, and provides portable primitives like reduction and accumulation. And this talk is about the last line, so my package. And I want to claim that in Julia, you don't have to pick between efficiency, flexibility, and portability. You can have all three. So two numbers first on AMD and NVIDIA for accumulate function. So CUDA takes 45 milliseconds for on a list of on scan of floats of 1 billion float 64. For comparison, so accelerated kernel here, okay, I don't know really why, but it performs really poorly here, at least on an ACE A100 GPU. It takes more than 400 milliseconds. And the vendor is much faster, like, so if you take accumulation on cube, it takes only 10 milliseconds on this GPU, and kernel forge is within 5 or 6% of this. And we have the same picture on the AMD GPU. It is also within 5 to 6% of rock prim. Okay, so what you can already run today is, okay, so it's not really exotic syntax. It looks like what already exists in CUDA.jl. So you can use a MapReduce with your own operator and your own types. You can compute matrix vector, and you can sort sort a vector, okay? And every line here is supposed to run at vendor speed, at least on tested architecture. I'll come back to this later. Okay, and where really Julia earns its place is here, because in fact, so it's as in qda.jl, you can create your own struct or tuple of struct or anything, and you can basically sort on any of your struct. And for example, if so, usually matrix vector product is supposed to run on, for example, float 32 and min and plus ring. And if you replace min and plus and times, and if you replace plus and times ring by min and plus, you get the tropical semi-ring. And so you can run it with any operator that you want. Min and plus is, for example, widely used in optimal transport. This is called the tropical semi-ring, I guess. Okay, and the sort function here routes to radix sort. So this is the sort algorithm from NVIDIA for Float32, and to sample sort if you use an exotic comparator operator of comparison. Okay, so in the Julia stack, you get basically kernel abstractions, which allows to lower any kernel to 4 backends. And on top of that, I added kernel intrinsics that provides some missing operators that missed from kernel abstractions, and kernel forge that provides these primitives, so reduction, accumulation, sort, etc. So this is the same kind of thing you can see in accelerated kernel. Okay, so mainly there were 3 things missing in kernel abstractions, I guess. So there were discussions on the Julia community. I saw a few of them. So for, warp shuffles, which basically is means exchanging registers between exchanging values between threads in registers. Ordered memory access, so that blocks from the same GPU can cooperate with each other, and vectorized memory access to saturate the bandwidth. Okay, so take shuffle operation. You can, so with kernel intrinsics, you can just write a macro and specify the direction, so up, down, or XOR, and the value to exchange this val between threads in the same warp. And if you get into qda.jl or amdgpu.jl, in fact, shuffle is the basic operation is reduced to 32 bits operation, and qda.jl already extends it to other types like complex, integer, uint, 8, etc. So in fact, you can easily abstract this stuff into any bits type using generated functions and multiple dispatch from Julia. Okay. Okay, so the architecture is 2-layer. There is a kernel intrinsics providing missing intrinsics, and kernel forge on top of that provides these primitives. And just to mention, kernel intrinsics, there was a little problem naming. Kernel intrinsics is not okay. Kernel interface. Kernel interface is it's not the JL, but it's a submodule of kernel abstractions, and first kernel interface from kernel abstractions was named kernel intrinsics, but okay, it's just a problem. It was just a little problem of naming. So for the primitive, basically I started with the map reduce, and my first goal, in fact, was to just to do the MapReduce function. It was just an exercise, in fact, just writing MapReduce to understand how a GPU works, and I wanted to do it in a single pass, single kernel pass. And you can do this only if you get the communication operator between threads. So what I mean is you need, yes, you need fence so that block cooperate with each other. Okay. So one block does a reduction, then it puts it releases a flag, and to warn other blocks that they can use the aggregate value. Okay, so scan, I won't enter into too much detail. It's just accumulate in Julia, and it uses a decoupled logback algorithm from Merrill-Garland. So, okay, it's the state-of-the-art algorithm. And sort function is based on radix sort. Okay, so this is one sweep, and this is within. So actually, in currently in kernel Forge, it's within 5 to 6% of cub and rock prim. Okay, so back to flexibility with one number. If you can take, if you want, you int 8, and if you want to reduce it, you can measure performance, and it's actually, if you want to accumulate you int 8 with after conversion to float 32, you get pretty close to cub, which when you make it reduce, you int 8 without even converting. So it can be pretty useful if you want to compress some networks of float 32 or things. Okay, and basically tuning is just dispatch, and so yeah, you dispatch to constants, to tuning constants. And instead of hand tunings, I'm working on auto tunings, but it's another story. I won't get into many details. So benchmark are measured with events. CUDA events are AMD GPU events. And basically, so I want to reach a parity with the vendors on, or better on all on these architectures and on these primitives. Okay. So there are limitations. It's untested on many architectures. If you try it with your own GPU, you won't get to vendor speed, but that's why I'm working on auto-tuning also. And it's not tested on Metal on one API. Okay, so thank you. So to take away, so I want to build an efficient, flexible, and portable library. I think that there we can close the gap between between vendors and Julia, while keeping a library flexible. Okay, thanks. Okay. I am not using what? Ah, okay. So I was not aware of it, so I recorded it. And do you handle the do you handle alignment also? Okay, so I'm not. I searched. I searched it. I didn't find it. I'm sorry, but okay. Okay. And does it fall back to tuples also if you cannot vectorize or? Okay, because basically I think that the function I use is just a LLVM pointer in the end. That so
Okay, yeah. Yeah. In the end, I use like there is a CUDA extension and an AMD extension, and there is I don't think you need the extension in fact for this, and there is a vectorized load, and there is some abstraction to handle the alignment, and that's all. But maybe you did it actually. Yeah. Yeah. Okay, so for now it's an experimental library. I would say, and I say if you want to compute like matrix time the vector with a fancy operator, I would say it may be faster than what exists currently. Or if you want to accumulate, it is an A100, and later on other architecture would be faster than accelerated kernel. Sometimes it's just for performance. Okay, so I really.
Okay. Okay, now. Good. All right, so good. Okay, so I'm giving a talk about separable function, and the question is a bit whether this is very relevant for the GPU community, because things are a bit different on GPU than they are on CPU, as you will find out. And so what is it about? Well, some functions, for example, a Gaussian, as you see here, are separable in the sense as that you can write it as a product of a function of x times a function of y in 2D or in 3D or whatever number of dimensions. And you can exploit that, of course, in calculations by writing your function as separables. I'm sure many of you have done it um, by yourself. So the question is, why do you need a package for that? Well, you don't necessarily need one, but it is useful to have. And so the idea is, can we somehow encapsulate this separability in an array class, basically, so that you have some object that behaves like a 2D array and feels like a 2D array, but is a separable object. And the idea behind this package. And so what are the advantages? Well, normally your code is not very memory friendly if you really compute a two-dimensional array, because that has a lot of values and you don't necessarily need them because Julia has a fantastic broadcasting system, right? So you can write it much better as a product of x times y. And also some function, for example, the exponential, and in particular the complex exponential, like a sys function, are quite costly to compute. But this does vary between GPU and CPU, because in a single, if you don't have any memory transport, then it might not cost you so much to compute it in every kernel, whereas if you do that sequentially, that is very costly. And so, well, you can use the separability as you see here, and it is written down here how you would basically factorize that. And then you basically have a number of one-dimensional Gaussians oriented along different dimensions. So this code here is not to be taken too literally. And then you just multiply the stuff together to obtain your results. So I think this idea is clear by now. And does it help you? Well, it does help you a lot because the generation is extremely fast because you need to, let's say, only calculate the stuff for 2000 value rather than for a million values, for example, if you have a 1000 by 1000 array. So that's, of course, much quicker. And then you're storing these intermediate arrays. And now you can wonder, do we actually need this separable array class? Because I don't know, can I get a show of hands who's ever written an array class yourself? Yeah, it's usually not fun, right? At the beginning, you think it's great, and then you discover all the problems over time that doesn't work. So array classes are a bit of a pain. And it turns out you don't need that. Why? Because it's already there. And this maybe not so well-known object called base broadcast broadcasted is in fact exactly what you want. So if you're somehow able to generate this broadcasted object that already behaves in all respects like an array and does everything you want, and it fuses with other broadcasted objects. So the idea was let's use that type and just make a package that generates these things for you so you don't have to remember how to use broadcasted. And you essentially getting all this laziness for free, so reminded me a little bit about the opening talk we had about Haskell. So here we have the laziness, right? And you can even reuse the memory because you can write into these things. So in this package, there's basically 3 versions how to do it. Version number 1 is just, it actually generates such a broadcastable, but then at the same time collects it. That can be still pretty advantageous because the calculation can be quicker as you are avoiding the, let's say the Gaussian. You don't need to evaluate the exponential every single pixel. You just do it once along x, once along y, then you're multiplying the 2 values together. That's faster than doing it, evaluating the exponential on every pixel. Then the second version returns this broadcastable object. And the third version, there is a class called lazy arrays that you can also use that is able to just defer the collection essentially. And we can compare with that. And nowadays, they are almost identical, the 2 performances. In former times, the lazy array class had still some issues with the speeds. And so that was usually quite a bit slower than just the broadcastable object. But I think nowadays, it doesn't make a big difference anymore. So how would you use it? You say Gaussian sep, and then, for example, you can give the parameters. It generates your separate Gaussian object, and you can store it, and it has relatively little storage space because it just stores these individual things. And then you can collect it, or you can just use it as any other array, and it broadcast fuses with the rest. Well, once you've written this, you're starting to wonder, what does separability actually mean? I mean, classically, you know this for multiplications, but you don't necessarily have to limit it. It could be an addition, or in fact, something as complicated as a complex number generation. So let's say if you want to write a Mandelbrot calculator, you can just do it as a separable object of imaginary and real numbers and add them together. So it's a real axis plus an imaginary axis gives you a 2-dimensional field, and you don't need to store all these values. You just store them separately, and whenever an element is accessed, the broadcast does it for you. So yeah, what is really inside it? So it turns out this broadcastable has some fields, which are the args, which are actually the 1-dimensional arrays. They are already pre-oriented in the correct directions. Then there is these axis numberings. So these are the base 1 to something objects. So essentially be iterables. And then the operator that connects all the things, that could be a multiplication, but can also be a plus or whatever. And then there's a broadcast style for it. And yeah, if you use it, it gets consumed. And as I already said, there's automatic broadcast fusion. So the simplest way is that you just say, my result might be a pre-existing array, maybe generated via similar, and then you're just writing to it, and then it is essentially memory free. Under some conditions, you get some overhead of 144 byte. I'm not exactly sure what that is, but under some other conditions, I don't get it. So it's a bit, I'm not sure what that reason is, but it's anyway, it's not an array, it's just some intermediates. And yeah, you can collect that. Let's move now onto the application with also on the GPU. Once again, what are the advantages? You don't have an intermediate array. It's seamlessly integrating. There's one fused kernel, and you allocate it once and can actually even reuse that, as I mentioned. So here's some speed measurements, and that gets a bit interesting because you see the red bars are the no CUDA, so the serial computation on the CPU, and yet there you see the relatively significant gains you get from in-place computation with the Gaussian, for example, to separables assigning, or with lazy arrays makes no difference, and so on. And if you then go to CUDA, it's even the opposite. You see, this is slower, right? So that's not necessarily what you want. And that is because as you see here, it's almost 2 times slower. The reason is that I was using as the indices Cartesian coordinates and or the Cartesians, and the Cartesians are generated in place in this particular case. That means there's no memory transfer to the kernel, right? So everything is generated right on the spot. You don't need to transfer memory, whereas that's not the case for the separables. You have to first bring this data in. And that's, I think, the reason why it's a little bit 2 times slower for this particular example. The question is, can you go further? So what about functions that are not really separable, but they are radial functions? So any function that is just a function of the distance from the center, can we use that? Not necessarily. It's usually not separable in x and y. But it turns out you can still do some tricks. And so this is what is shown here, and it's actually also part of the package. And so I want to draw your attention to these 2 boxes here. So you can, of course, say, well, even though the function is not separable, if I have the square of the radius, that by itself is separable, Euclidean thing, right? X squared plus y squared gives you r squared, and therefore you can write your function in terms of r squared and then use r as a separable. This can help you a little bit, but the other approach to that is we can actually exploit some symmetries in the data. So that means if you have, for example, a 2D data set, you can say, I just need to calculate one corner of the data, and all the others are just index flips, right? So you need to calculate it once, and then you can flip it, and that can also help you. So this is implemented in one of the 2 versions, and the other version is actually really using interpolation. So you're just calculating a one-dimensional thing, and then you're via interpolation getting the individual pixel values, which can sometimes work. And one trick is that you just calculate that one line with a much higher resolution so that your interpolation errors are rather small, right? So you're 8 times super sampling, for example, and then when you're asking a particular pixel, your interpolation is actually pretty accurate because you've super sampled so much. So in summary, you are using a lot less memory, and I think that's also for the, let's say, CUDA community here, the biggest take home. You can avoid a lot of memory by storing these separables. And yeah, then there's these radial tricks that I already talked about. And yeah, has it been used? Yes. The biggest use, I would say, is, for example, a complex shift operation. E to the I kx as a vector is also a separable function. You can write it as e to the I kx x times e to the I kyy times e to the I kzz. And that buys you a lot of computations, in particularly on the non-GPU cases. So that's a very useful operation where this pays off and is a lot faster than calculation on the spot. And I think that's pretty much what I wanted to say. Here's a few examples, also some examples that are non-multiplicative. So phase would be, for example, one of them. And also a nice bonus is a bunch of functions are in that package. For example, window functions. So if you need a hand window or any other window, you can just write a separable thing and it's in there already. Okay, so that is my talk, and then it's time for questions. So what I was referring to, I repeat the question. So you were saying, where does the number 50,000 come from? That I was quoting. No, sorry. So the separable array stores an x vector and a y vector, which is in this case also a z vector. Whereas the full array stores every single element in 3D. Right, and that's of course way bigger. So it's the product of the three sizes rather than the sum of the three sizes, which makes a huge difference.
Yeah, hi everyone. I'm one of the developers of Speedy Weather, and over the last year, we basically had, or like a year ago, we had basically a lot of the basis set up so that you can run it on the GPU, but we hadn't actually like gotten there because it turns out climate modeling isn't that as easy as you may think. And so it took us a while, but now basically we have the whole GPU acceleration. And I wanted to give a little bit of an overview talk of what we did, how we got there, how you can use that, and maybe there's some parallels that you see to your own work. Feel free to reach out for any of these. So Speedy Weather, we kind of name this as like the user-friendly, fast, and flexible climate model written in Julia. There's a bunch of things you can do with it. Just as an overview, you can also couple it to shenanigans that I think a lot of people in the GPU community are aware of. But basically, we do solve things numerically in a quite different way in the atmosphere because it is a spectrum model, but it's also part of numerical Earth. So we also have coupling to like Terrarium, the land model that is based on shenanigans. And we are also working on the differentiability with enzyme and reactant, but there's other talks throughout the conference here where people have talked about this. And we basically mostly see this as a test bed for ML parameterization. So basically trying to reduce the uncertainty of climate models, exploiting the modularity of the model and kind of like playing around by replacing individual components with something that's, for example, learned. But the whole thing obviously still has to be fast and differentiable and so on and so forth. Just to give you one video to illustrate a little bit the complexity of this. So solving Speedy Weather has weather in the name, so it has the focus definitely on the atmosphere, but it also has a relatively simple representation of land, the ocean, as well as sea ice. You can see some of these features here, like the sea ice edge, how it moves further down. You can see heat fluxes over land. So whenever the sun, you see the daily cycle basically moving through there. Whenever the land is warm, it obviously warms the atmosphere from below. And then you have these weather systems like low and high pressure system moving through. A lot of turbulence around mountains, and this is kind of the whole thing that we're trying to simulate, but obviously in a very easy and user-friendly way. Because we kind of took a lot of inspiration from shenanigans here. So our GPU user interface really starts with, like you say, using Speedy Weather, using say CUDA, or using AMD GPU, or using Metal, even though that we haven't really, that's still work in progress. And then your GPU function basically is being extended. And so you just, whenever you create the grid, you call here the spectral grid because it's we have a spectrum model, you literally just put in architecture equals GPU. And that passes on information when you create the model, when you initialize the model to have the simulation with all the variables, which array type to actually use. And then running the simulation is as simple as just putting a run and simulation in front of it. So you can really do a whole GPU simulation in these lines of code. And the only thing you have to change is swapping a G for a C if you want to have the same thing running on the CPU. And so we had to put a lot of work into creating basically array wrappers. So here you see this like octahedral Gaussian field. So basically to have a wrapper around, then basically the data inside is then represented in this case as a Q array of some dimension of some type. And that way you can basically interact with everything as it was before, and under the hood we're replacing one array type for another, and the same then also works for the element type, right? We basically calculate everything in single precision, so that works fine, but you could also do it in double precision, but you could also come up with your own custom number format if you wanted to. The equations that we're actually solving is relatively complicated. If any of you have like a physics background, It's basically a form of the Navier-Stokes equations, but adding a few other things as well. So not just temperature, technically there's also humidity in there. This is actually not the form that we're solving, but just to kind of, if people have seen these kind of equations before, it's a bunch of processes in there, advection, Coriolis, gravity, pressure gradient, viscous forces, conservation of mass, ideal gas law we have in there. We have things like adiabatic conversion, but also actually where I wrote the C sources here is actually like one letter for to summarize a lot of other things. Because there's many processes that we can't explicitly resolve, so that are not represented by this like form of the Navier-Stokes equations that are happening basically in one vertical column of the atmosphere. So there's like sun shining in from above, you can have precipitation that basically falls vertically. And the same you would have near the surface where you have like boundary layer turbulence and you have then fluxes of like heat or humidity coming up into the atmosphere, right? And so even though these equations already look complicated, what's missing is humidity, clouds, precipitation, snow, radiation, surface fluxes, ocean, land, and so on and so forth. And to make the whole thing even more complicated, what we're doing is we're actually not solving all of these equations in grid space. So we've seen a lot of talks around like stencil operations where you usually think about like a grid and then you have a left neighbor, right neighbor. We're actually solving roughly half of these equations in spectral space. So you can really think about applying a Fourier transform to this. And in some cases, you just swap the operators. And so some of these, let's say, the time stepping, for example, is done in spectral space and not in grid space, meaning that we also have to deal with complex numbers. To kind of try to break this all down, we have roughly order of 100 custom kernels, 30 to 60, depending on the complexity of the model that we're solving, are hot, meaning that they're basically being executed on every single time step, and they have a bunch of varying requirements. So if you kind of think the whole variable state as a massive matrix, so kind of like in X, Y, so the horizontal direction as well as the Z direction, so that maps to columns, rows and columns in the matrix, then the first thing that we would always calculate are the parameterizations. So the stuff that happens in the atmosphere in the vertical, and that basically maps then to the rows here. So we have a kernel launch here over XY, have things like loops in the vertical, but we also have conditionals. Okay, that's not really the problem. But what we definitely faced was we wanted to have fused and modular kernels. I'll talk a little bit more about this, but it has a lot to do that we want the users to be able to have a quick access to change things there, but still run things on the GPU. Without actually them knowing any of the details. As the kind of the next big step is like what we call like the dynamical core. So that's basically solving your Navier-Stokes equations. Some of these kernel launches here just like over X, Y, Z. So they're really like just like for each element you do something. That's not too complicated. So I won't talk much about here because we basically just use the typical kernel abstractions here, and that's fine. And then the third one, and this is one of the like kind of major things where really we spend roughly, depending on the setup, but roughly like 50% of our compute time is spent in these transforms, so going between the grid and the spectral space. And to make the whole thing more complicated, we basically have different blocks in X, Y that are of like different size. And within these blocks, then what I try to illustrate here with these vertical black lines is basically, you can think about this as that there's a Fourier transform applied in this part, but these Fourier transform would then have different sizes, but there's actually also a Legendre transform applied that is then kind of like, does it even in a different, slightly different order. And so we had to use the CUDA graphs that actually only a couple of weeks ago got really fast, thanks to all the work that Max put in. So it's batched in Z, actually also batched in the variables. And we also have to deal in here, obviously, with complex numbers. And so for the next slides, I kind of want to talk a little bit about the first part, the parameterizations, focus a little bit of how we did this like fused and modular kernels. So that's also easy for the user to extend this, as well as talking a little bit more about the transforms. So the modular kernel fusion, basically, that was a problem that arose because in the end, kind of really breaking it down, we wanted to have something where, or like illustrating the problem. Imagine you have a kernel that you launch over some indices, and then you want to call different functions after another. So let's say f, g, h, acting on some variables. But the user may also want to say, actually, I don't want to execute f and g. I want to execute them in a different order, or I want to execute slightly different ones. We still wanted to have this fused as a single kernel because essentially each of these really just act only on the index ij. But we also wanted to have an interface where someone could relatively easily say, I'm just writing this like custom function in there. And we wanted to have this all fused together. So the way how we, in the end, for us solved this is that on the GPU, we launch the kernel over IJ, but then we iterate over these kernels. So like we would say FGH, and we actually did this with these generated functions. So we basically have a tuple of symbols in like the name tuples that we then use to generate this function at compile time. So it basically writes us this down, and then this can be launched, and that works then as well for like swapping the orders. So like as long as you create this name tuple in a different way, when you create the model, that works. But also people can then basically write their own new types, and basically as long as they hook this in and it ends up as this name tuple, then that also works. On the CPU, what we found interesting is that actually you want to change the order. So you don't want to launch over IJ and then iterate over the kernels. You want to iterate over the kernels and loop over IJ within it. And so within these generated ones, we basically just changed the order. And this is code that's completely hidden from the user. But I found it really nice that within this framework, we can basically, even though we do like CPU, GPU flexibility, we can also change the order without changing anything inside the kernels themselves. The spherical harmonic transforms on the GPU are basically the beast that probably took us most of the time to do things, because the spectral space to represent the spectral space, we had to come up with this package called lower triangle arrays, which really doesn't even store zeros for the upper triangle, where we really just don't store anything there at all. But we wanted to have it like an n-dimensional array that also can extend in the any kind of additional other dimensions. We use the spectral space for any kind of linear operations. So like multiplying with a constant, adding something together, computing a gradient, computing a Laplace operator. So you know this from the Fourier space, where it's really easy to compute a gradient. This is also the same, also true for the spherical harmonics. But there's other operations that are much easier to do in grid space. So for example, doing like a element-wise multiplication or addition, you do then in grid space. However, we've seen a bunch of talks where people always represent like multi-dimensional arrays as nice blocks. We don't have that because things are getting a bit narrow towards the poles, but they're a bit wider around the equator. And so I'm just illustrating this here as these big circles with like north at the top, equator in the middle, and the south pole at the bottom of this circle. And so basically over these black lines, we have to compute our Fourier transforms. And so they are of different lengths. So at the very top, there would be 4. And then depending on your resolution, you can have length of these Fourier transforms going to like 1024 or even more. And then you basically ramp down again once you get to the South Pole. And so we also ended up with things with tricks like that we actually treat the additional variables just as like kind of like an extent. We basically just fuse them in the vertical dimension. So when you compute a transform of several variables, it basically just like we just computed once over the kind of like fused array. And so for these, like, because of these different lengths, we definitely have to use QFFT on the CPU. We would use FFTW. But then in the graphs were really, really important not to end up with a lot of like small kernel launches and kind of balance the whole thing a little bit better. And so, yeah, Max did some fantastic work there to make that fast. We actually also employed a little trick. I think computer scientists always get excited when you say like fast Fourier transform, it scales better. But it turns out for low resolution, sometimes it's really beneficial to forget about the fast Fourier transform and basically treat the whole thing as a massive matrix multiplication. And so for that, we also have a version where we actually use the normal fast version in order to pre-compute all the entries of this matrix, and then basically just have a massive matrix multiplication, especially at low resolution on the GPU. That works really, really well. And just to illustrate here again, this idea of like the batched vertical and fused variables. If you think about different variables like U, V, T, Q, P, we basically just treat them as like subarrays of a big array. And then instead of having like say 5 kernel launches, you would just have 1 over the whole thing. And that makes it really efficient. Just to illustrate this a little bit in terms of performance, on the x-axis here, you have the resolution going from low to high. And on the y-axis, it's the speed. And the speed is therefore like higher is better. And so where we currently are comparing to ourselves with the CPU is basically that at low resolutions, we get like 6 times faster. That's at least good. Okay, we're not actually like fully loading the GPU. That's fine. And at high resolutions, we're treating about like, we're getting about like 50 times faster, which is fantastic. Comparing this to, which is not apples to apples, but the most similar model that's written in Python JAX, we kind of get comparable performance, but we're definitely better at low resolutions. We're a little bit better at the high resolutions. We definitely have to put more work into this to figure out what's actually happening. But as I said, this is really not an apples to apples comparison because a lot of things in the numerics are actually quite different. And also, for example, we compare here like one CPU with versus 32 for them. And so just to sum up this, we're always happy to collaborate. I believe a lot of people here are really interested in like GPU performance. You could use SpeedyWeather as a test bed. We're always happy to collaborate, or for your own projects, look into how we did these things. Reach out if you have any questions. Thanks for listening.
All right. I will today, I'm Tim, I work at Julia Hub, and today I will be talking about a package I've developed and released this year called qtile.jl, which makes it possible to program NVIDIA GPUs using a new tile-based programming model. Before that, maybe it's worth explaining why we need or why we're interested in a new programming model. So typically, if you want to develop parallel software, you have to be thinking at three separate levels of abstraction. So at the global level, for example, you're processing an image. The global level, you're using coarse operations like a scan, a reduce, a broadcast over the entire image. In order to implement that, you typically decompose those coarse operations into independent tile-based operations, which are only then implemented using the parallel hardware at the thread level that a GPU has to offer. So for example, if you want to do this with CUDA.jl, say you want to implement an operation that the package doesn't currently provide, you start by implementing one or more kernels at the grid level. I'm using CUDA terminology here. You decompose that into problems you implement at the block level, and only then at the thread level, you'll be using all of the parallel hardware that the GPU has to offer. The problem is that this decomposition is typically a fairly hard thing to do. You have to think about how do I move memory from the global GPU memory into what my threads can access. You have to think about how to order that memory, what the layout is, how you access it from the kernel. You have to think about where to store it. You can store it in registers, you can store it in shared memory, you can store it in specialized memories like tensor memory, and so on and so forth. And then finally, only finally, you're thinking about how actually to compute things, and that interacts with all of the previous decisions you made. So it's a whole deal, and NVIDIA realized this. So this year they released CUDA Tile, which is a framework by NVIDIA, making it possible to write programs, GPU kernels that only think or require you to think at the block level. The compiler, the framework, will take it into its hands to do all of the tricky decisions like how do I move memory, how do I store memory, and what compute strategy to use. And to make this a little more specific, here is a transpose kernel, a fairly straightforward operation implemented using CUDA.jl, using blocks and threads. And for somebody who hasn't written GPU code before, this is probably fairly daunting because we have to think about lots of things here. As you can see, I'm doing it slightly tile-based. I'm staging those tiles in shared memory. So I've decided to use shared memory. the size of that shared memory is padded. You see tile plus one comma tile. That's a decision to avoid bank conflicts when accessing the memory. We have to synchronize because the kernel contains two block level operations. All of the indexing operations in here have been carefully chosen such that subsequent threads, memory accesses are coalesced over these threads. So there's a whole bunch of complexity here that generally you would not want to deal with. So the tile version of this transpose kernel is essentially this. We have two indices, two block indices. We use that to load a tile, we transpose the tile, and we store the tile back. That's it. No low-level complexity anymore. You can fully think and reason at the semantical block level. And the performance of this implementation is identical to the one I showed on the previous slide, which is, yeah, interesting. So if you want to use this practically, I've tried to make qtile.gl as similar as possible to CUDA.gl. So you can simply install it with the package manager. It will download all of the artifacts that are required. One gotcha is that it does require slightly more modern hardware and software. So you need a driver that's for CUDA 13 or upwards, and you need an Ampere GPU or upwards. That's every 30x consumer GPU or an A100 up. So Turing and Volta are not supported. If you then go and write a kernel, for example, a small vector edition, and I've grayed out the kernel code here because I want to focus on the host interactions, you can see they're completely identical. So the Q arrays we have in CUDA.gl are equally usable using qtile.gl. There's no difference. You can even reuse the add CUDA launch macro. The only difference is that now there's a backend argument, and you can use that backend argument to specify that qtile has to compile the kernel. And the threads keyword argument also goes away because now CUDA tile itself is responsible for determining how many threads to use to launch your kernel. And then looking at the kernel code itself, you can see, and this is obvious, there's a couple of new functions and intrinsics that you have to know about to write CUDA tile kernels. For example, there's ct.bid, which is similar to the block ID and the grid dimension and all of those intrinsics that you're already familiar with from CUDA.gl, but now at the tile level. There's ct.load and ct.store. Those are the two most important functions because they load and store tiles. There's atomics, there's some specific functions like gather and scatter and arrange to initialize a tile in the same way that the arrange function in Python does. But all of the other CT qtile specific functionality that exists in CUDA.tile Python, we've tried to express as much as possible using existing Julia functionality. For example, instead of ct.full, which is a function in CUDA.tile Python, we just use a fill function, and so on and so forth. So with method overlays, we make it possible to reuse as much as possible of the Julia language that you're all already familiar with, and just repurpose that for use within a CUDA.tile kernel. It's also worth having a quick look at how the compiler works. So recall, for those of you that are not familiar, the existing CUDA.gl compiler actually reuses a lot of the Julia compiler by virtue of being able to piggyback off of the LLVM code generator and then just pass that LLVM down to the NVPTX code generator, which generates NVIDIA-specific PTX code. This is beneficial because it allows us to, well, reuse Julia's code generator. So we get new features in Julia for free in CUDA.gl, mostly. QTile is different. So because tile IR is basically MLIR based, we've had to, we cannot piggyback off of CodeGen and reuse LLVM IR, but we have a new code generator written ourselves that starts from Julia's IR, raises the level a bit to reintroduce control flow, and then does all of the optimization required to emit MLIR code. The problem with this is that because of not reusing the existing Julia code generator, we do not get all of the features that are implemented in the Julia compiler for free, which practically boils down to that some codes that works in CUDA.gl will not work in qtile.gl yet. We're going to work on that. We're going to improve that. But if you're just going to try and throw a whole package that works with CUDA.gl because of all of the nice composability and throw that at Qtile, it might not work. So if that happens, try to reduce it to the feature that doesn't work, file an issue, and we'll take a look. In any case, you can use reflection macros again for those of you that are interested to have a peek behind the scenes. So we have this add device code structured macro, which shows the structured IR that Qtile has. So structured meaning control flow has been raised. You can see there's a for loop instruction in there. And you can also look at the tile IR that we generate and we hand off to the NVIDIA compiler. And this is just to show that the code that we generate is similarly as with CUDA.gl, pretty high quality. And comparing performance to Qtile Python, we actually beat or exceed the performance of the reference implementation on most benchmarks. And those benchmarks are part of the repository in case you're interested. And because of performance being pretty great, we're of course experimenting with actually using this. But because of the raised software requirements, we're currently still doing this out of tree in Qtile.gl, not in CUDA.gl. But you can play with these implementations by wrapping your Q rates with ct.tiled, and then you'll get some of the optimized advanced implementations we have in Q.tile. For example, broadcast with CUDA takes, this broadcast takes 11 microseconds. With Qtile, it takes only 5. It's interesting that even a very element-wise function performs faster, even though it's not using the tensor cores, but that's because the tensor hardware also has a tensor memory accelerator, which can load memory in a different way that apparently can be faster. And we also have reductions implemented, which are also a nice couple of microseconds faster. If you're interested in any of this, I have given a webinar together with NVIDIA a while ago. That's what the QR code links to, which is basically a much expanded version of this talk with more details, more benchmarks, an elaboration on how to implement matrix multiplication, and so on. I'll be tagging 1.0 of Qtile.gl very soon, hopefully this week. So I would all recommend you to, everybody with an NVIDIA GPU, take this for a spin and let me know how it works. Thanks. The question is of whether it would be possible to emulate tile-based kernels with other backends. Okay, it would, but it's a very complicated compiler. I mean, either we want to implement all of these optimizations ourselves in MLIR, or we could provide a very simple way to just run them correct. The former, I'm not going to attempt. I'm hoping that the vendors themselves are going to copy this and put something out in the next couple of months. So personally, I don't think I'm going to work with this. I'm going to wait until the vendors catch up. And in the meantime, we can experiment with Qtile.gl. And once this is mature and we get new backends, we can try and abstract it in something that's reusable across other backends. Question? I'm going to, yeah. Yeah, the question is about compatibility with Enzyme because Enzyme runs on LLVM IR. Yes, that compatibility is currently absent. So probably this will either take Enzyme optimizing MLIR or a lowered form of these kernels or having custom rules for these operations for now. This is currently not yet in scope.
Just a brief comment about the question before is that enzyme MLIR exists and it's what we use in React. And so it can be added. That support can be added, but
the question is whether it's basically so that the only thing you had to do to port kernels is to load tiles and then keep all of the operations in between the same and then finally store a tile. That's basically correct, except that of course your algorithm may have to be adjusted because all of a sudden you're working with groups of data. It's not scalar data anymore, it's actually a tile of data. So for an element-wise kernel, it's probably easy enough to go from element by element processing to tile by tile processing. But as soon as you have something cooperative in between or some more logic that assume order within the tile, then you'll have to adjust your implementation to work on tiles, which are basically, I mean, you can choose the size, but it's typically like 32 by 32 elements rather than scalars.
Okay, so the next speaker is me again. Um, is this 1 second? So assuming my laptop doesn't lose power completely, there we go. We're going to be discussing just a general quick status update about CUDA.jl, all things that are not Qtile. Sometimes when I'm not doing tensor networks, I do CUDA.jl PRs, much to, I guess, Tim's grief. Uh, So we're quickly going to talk at a high level about what's happened this year with the package, and then move on to discussing some exciting developments coming soon. One thing that is pretty exciting about CUDA.jl, which might sound a little strange, is that the package is pretty mature. So ideally, we don't actually have that many updates. And hopefully the updates we do have are good. So some of the main ones, we now support CUDA 13, and we finally dropped support for CUDA 11. If you are like me and really cheap, and you still have like a 1080 or something, I guess that's painful for you. But also those GPUs are 10 years old, so we finally no longer support them. We have support for upcoming Julia version 1.13, and we support 1.12. And we are at least running CI on nightly, so someday we'll support 1.14. Hooray. One really big change that you probably noticed if you depend on CUDA.jl is that we finally split up all of the CUDA libraries into separate packages. And we also now have sort of a core library that basically just vends cuarray and then some of the logic we need for broadcasting that's not already covered by GPU arrays. So people who've been around for a long time will recognize that this is really ironic because it used to be that all of these packages were separate, and then we sort of like glommed them together under CUDA.jl, and now we've split them up again. The benefit for you as a user is if you just want to write kernels and you don't care about all these vendor libraries, you don't have to worry about them. You can just write your kernels and live your life, and you don't have to sit there watching a 500 megabyte shared object file take like 30 seconds to DL open. Or if you're like me and you just want to use cuBLOS and you don't care about cuFFT, then you only have to load one of those very gigantic shared object files. So hopefully from a usability perspective, it improves life for many people. I know the upgrade process for some was kind of rough, so hopefully that is now dealt with. And we've also added support for the new block sparse sublibrary in cuTensor. I tried to call people out specifically in this who made a big contribution. If I forgot you, I'm really sorry. We've also made some quality of life improvements in general. We have a lot more benchmarks for array operations. You can thank Christian, who's our next speaker, for that one. We made the tests a little bit memory intensive. Anyone who's tried to run the CUDA.jl tests know they take a really long time and they're very memory intensive. In a way, it's a good thing because we have pretty comprehensive test coverage, but it's also a really good excuse to like watch something on Netflix because they take a long time. And again, if you have an older GPU, it really is quite painful because we run a very large number of different configurations of arrays, for example. As we mentioned earlier, we are also adding slowly but surely more support for array wrapper types. So of course, one of the selling points of Julia is that you all have all these wonderful wrappers. You can give Julia information about the kind of matrix you have, like you know that it's symmetric or something or diagonal. There wasn't necessarily such great support for those interfaces in CUDA.jl, and that's slowly improving. Some of that is happening at GPU arrays, but of course, because cuBLOS especially supports a lot of the more specialized functions for like gem, but it's symmetric, or matrix solve, but it's symmetric. We're now having like a little bit better plug and play for that, or things like matrix multiplication. Again, anybody who has, I guess, followed the trajectory of CUDA.jl's project at TOML knows that the profiler was really having a struggle earlier this year, and now it's substantially better for a variety of reasons. So thank you to everyone who helped with that. There were quite a few people, so I didn't want to fill this all with GitHub usernames. And folks have also been working really hard on removing unnecessary allocations and some low-level operations. So you should hopefully notice things like kernel launches being a little bit snappier. Or maybe you won't notice, but they will be snappier. So that's nice. Another really big change was that we finally moved some of the sparse array functionality into GPU arrays. So CUDA.jl and AMD GPU.jl had about like several thousand lines each of almost completely duplicated code for handling sparse arrays and broadcasting over them. Obviously, this is a very easy source of bugs, and for better or worse, AMD GPU replicates a lot of the cuSparse API. So but we, mostly me, decided that we should just move some of this into GPU arrays.jl. Some benefits of this are that we can use common infrastructure for handling broadcasting over sparse matrices. It means that we should be able to extend support to Metal relatively easily. It also means that we can test a lot of this with our handy dandy tester library JL arrays, which is nice. The downside is that it was a very large change and kind of breaking, and other folks, i.e. like Guillaume's lab, had been working hard on some GPU-based sparse arrays, and maybe they think our changes suck, which is very fair. So there's still a bunch to be done here. Currently, we only really support CSC and CSR format. COO and L are probably needed, so if you are interested in adding that, we're obviously looking for PRs. There's more broadcasting we'd like to support. For example, you can't really broadcast from a CSR to a CSC right now, I believe, and vice versa. And probably some of the code could be simplified pretty substantially. So if anyone wants to contribute to that, again, if you have like the sort of like intersecting um, problems in your brain like me that cause you to like both sparse arrays and GPUs, we're always looking for contributors to this. And probably also other backends like Metal would benefit from having something like this as well. So if anyone wants to add support for this for Metal, or maybe Christian will tell us that it's already there, that would be very welcome. And then I'll just quickly talk about what's coming down the pipeline, which should hopefully be very exciting for us. So one really big improvement that we have on the way, which is not specific to CUDA.jl, but we don't have an AMD update talk, so I'm going to talk about it first, is that we're hopefully moving very soon to GPU compiler 2.x in the tagged version. Why does this matter to you? Well, the main reason is that it will let us use the new very cool compiler caching.jl package. Why does that matter? This package has a really good name because it allows you to cache the results of compiling stuff. And mainly the benefit is that we'll be able to reuse compiled kernels between Julia sessions, which I believe is currently not possible. And we've had an open issue for this from like 2019, so pre-COVID, so basically like the dinosaur era. It also might mean that you can precompile stuff you previously could not precompile. We'll probably still have some time to first X problems because some of these are not really due to the kernel launches, but it should cut down on some of it, and we'll be able to tackle those once this is done. This is entirely Tim's project, but he wisely didn't want to, I guess, talk about it in front of the audience, so you can find him later and bother him about it. Because I actually don't know that much of the details, but it should be pretty exciting once it actually works. We also have a couple other things on the way that are hopefully useful to others. We have folks adding support for the new floating point types that NVIDIA supports. So there's a bunch of these, like, I don't know if I want to call them odd, but they're new floats with very, very small mantisses. And this allows you to do very, very high performance, sort of like neural network based computations. So if anybody here is an ML person doing, I guess, like normal ML that normal people do, this should hopefully allow you to write higher performance codes. Again, as we mentioned, we should have improved sparse support via these generic GPU arrays interfaces. So mostly that supports for now broadcasting, but of course there's lots of other operations on sparse matrices we'd like to support. There's a lot of lineage that we could, in theory, handle. Even things like we really don't handle broadcasting over the columns of a sparse matrix or the rows of a sparse matrix, depending very well or even at all. So if someone wants to implement that, that would be very, very helpful. And indeed, we should have more formats on the way soon. Partly because other people in the community want to use sparse arrays on the GPU and they can force their students to do this by feeding them good bread, I guess. Uh, we also hope to have better integration with Enzyme. Of course, there's also many people working on that in the community, but we're working on getting better support for actually testing Enzyme rules if you need to with CUDA. Hopefully, the Enzyme tests will soon work, especially once we tag GPU compiler 2.0 support. And we've also fixed some bugs that should actually allow forward rules for CUDA kernels to work, which were currently broken. We're going to hopefully keep removing these unnecessary allocations. And since this is finishing relatively early, hopefully we'll have some time for questions and discussion where we can get the opinion of folks in the room. Like, what is it that you want to see from CUDA.jl? If you have any pain points, please let us know. Or also let us know if you're like, no, everything is wonderful in my life. I just sit, and I eat peaches and cream every day and I run my kernels and nothing bad ever happens. So if you have that feedback, that would be wonderful too. And with that, I think that's all my slides. So thanks for your attention. And we definitely have time for questions. Anybody? Oh, okay, Rainer has one. So I'll just repeat it so it shows up on the stream. So apparently we now have support for Y direction FFTs, which is like a 10,000x performance improvement. I mean, well, I didn't run the benchmark, so I'm willing to say it's 10,000x, and I'm the one on the stream. So it's 10,000x. So also very awesome to hear. Anyone else have any questions, comments, feedback, requests? Oh, Oscar. So the request, I guess, was for factorizations, especially multi-GPU factorizations. So indeed, I think as the Dagger talk earlier mentioned, there are a bunch of like CUDA libraries that support these multi-GPU things. We basically don't wrap any of them, partly because it's just me and Tim, and I think also like Tim doesn't want to do it, and I don't have time. Well, that wasn't on the stream, so we won't. But it's definitely an open problem. Of sort of the best way to support that. So if someone is also interested in doing that, maybe as like a separate package, using Dagger or using some other library, that would also be very welcome. Given, I guess, that the two of us are like probably the main maintainers for this right now, we probably won't have time to do it, but it sounds like a really great project for someone else. So it sounds like if you really want to add multi-GPU factorization support, you should talk to Oscar. Probably got time for like one or two more. Anybody? Okay. If not, thanks again, and I think we can get Christian start like a minute or two early to tell us what's new with metal.jl.
Right. Hi everyone, I'm Christian, and I've been maintaining Metal.jl with Tim for the past few years. This talk I'll be going over a few of the changes since this was originally presented in 2022. I'd like to start with some of the major fixes that we've merged in the past few months because some of these are correctness fixes or silent failures, and you might want to be aware of them to update your code. Um, Two are related to uh, non-results in operations. These are both from upstream the metal performance shaders framework that we were using. So matrix multiplications, this was mostly seen on M1 and M2, but it apparently can happen on later. So we've changed the default matrix multiplication implementation to move away from MPS to work around this issue. Similarly, we used to use the MPS rand-n Apple provided number generator, but that also could return none on some seeds. So that's been changed to a native implementation, and if you're using the defaults, you shouldn't encounter this anymore. And then finally, the silent errors, large copies greater than 4 gigabytes, which is big, so you probably won't have encountered this, but again, this is upstream issue. PyTorch also works around this. We essentially just do more transfers chunked by 2 gigabytes, and so that's been fixed as of 1.9.1. And the other silent issue is grid size. Metal doesn't support launching with a grid size of more than essentially the type max for unsigned 32-bit integer, so 2 to the 32 minus 1. If you tried to do it, it would either hang if you requested exactly 2 to the 32, or it would silently truncate if you requested more than that. So now we error if you are attempting to do this operation, which is wrong. And I've gone around and fixed broadcasting to use grid stride implementation. Therefore, we're not ever requesting more than that. And then GPU arrays, fill, and friends, so the ones and zeros functions should be fixed. Just a PSA, kernel abstractions code doesn't expose grid strides very easily. So if you plan on working with arrays that are larger than 4 billion elements, you might want to verify that you won't be running these on Metal or AMD, or that you have a workaround in place, because AMD is also affected by this. Once we once we release kernel interface, not intrinsics anymore, it'll be easier to write code that can do grid stride. Now for new features, there's been a lot of work and a lot of new features, especially recently. The main group of features are enabled by MPS Graph, which is different from MPS. MPS Graph is Apple's MLIR-backed, MLIR-based, essentially, neural network acceleration framework. And so after I added Objective-C wrapper or partial Objective-C wrapper generator to clang.jl, it made a lot of this much easier because I didn't have to go through every single struct object and all of that and like implement it myself. So I started with matrix multiplication in 1.6. And again, this was to replace the MPS implementation that would return non-results. And as of 1.10, we by default use MPS graph matmul for every device and backend because we can cache the graph and that's always faster. Him recently added reductions, scans, and sorting backed by MPS graph, so those should be faster too. Sorting is a little bit more limited. It only supports the default keyword arguments. Also, FFTs, since I started contributing, this has been by far the most asked feature, and neither Tim or I are very familiar with them. So it kind of lingered until someone posted a PR that nerd sniped me into cleaning it up and merging, so thank you. And then nnlib extension. Again, Tim went and implemented via MPS Graph the neural network primitives and also added an extension to nnlib, which has been released as of 0.9.38. We also have, as of 1.10, 1.10 was a very big release. Most of these features are from a few months back. Metal.profile, but an integrated profiler. So now with the profile macro, you get just a summary of all the Objective-C calls and their timings in your terminal. If you want to use the old profile functionality, which was the Apple profiler, you can use the keyword argument external true. And then if you want your calls ordered in the order that they were called instead of how much time they took, the keyword argument for that is tracing. And then a laundry list of extra features. Simeon added device-side RNG for 1.9. We have logging as of, or well, print, which is also integrated into kernel abstractions as of 1.10 for macOS 15 and up. We added a bunch of linear solvers for linear algebra. We have thread fences, which is also a macOS 15 plus feature. Atomic memory order is a feature that will be supported in the upcoming macOS release. These aren't supported by Apple currently, but you have that to look forward to when it releases next month. We added a bunch of metal shading language intrinsics, such as SIMD Shuffle, XOR, SIMD Ballot, and the int16 versions of these, or the indexing intrinsics. And then also, since metal doesn't support float 64, a lot of operations that would widen to 64-bit float in base Julia will sometimes crash. So we've added a lot of overloads for functions so that these can be run on metal GPUs. Now, performance improvements, there's been many. Recently, 1.10 improved time to first kernel. On my laptop, as of yesterday, it was 11 seconds down to 1, which is great. And unfortunately, it comes with extra pre-compilation, but that might affect me as a metal maintainer more than it would you as the users. So I think this is great. Non-blocking synchronization, this is ported from CUDA very recently. Most of the time you'll be encountering the 2x speedup, which is just a small kernel that essentially completes instantly. And then if you're just synchronizing with nothing, no work to do, you can get these crazy speedups that make just like having them run in loops where nothing's happening quite a bit faster. More performance improvements, we have a native matrix multiplication. So for types that aren't supported by MPS graphs, such as int32 or something, we have quite a decent speed up compared to the default generic fallback in GPU arrays. We have a lot of launch improvements. These came from batch kernel launches. So now kernel launches will happen at synchronization points. So you can launch a few at once instead of having one call for each, which is expensive. And then something else that improved is a lot of micro optimizations in Objective-C, which reduced tiny allocations, and metal.jl also had a few improvements to the launch code. We also have improved memory management. So this now talks to Metal itself to get an idea of the memory pressure and calls the GC if needed. And then future work, I've been looking into dynamic kernel memory. And then once we have that, we can add it as an interface to kernel abstractions, which would be great. And then Apple has unified memory. We currently don't default to shared memory, as they call it, but we're looking into merging. I have a PR up, but I'm it it makes errors easier to miss because it allows some things that we don't necessarily want to be allowed in normal GPU code. So have to figure out some ways to better make sure that we're catching those before merging. And then 3 question marks is your contributions if you have any errors or features that Metal supports that isn't in metal.jl, please open a PR or issue and I'll look into it. I think the answer is no one's taken the time to add Float64 emulation to the package. Yeah. Oh, the question was why not emulate Float64 instead of throwing an error? A lot of those limitations are due to, I think, GPUs requiring specific alignment. So by creating it on via Metal directly, it handles those alignment issues. Whereas if you create it on CPU, you might not, the array might not be, like the backing memory might not be properly aligned. Yeah, essentially, if you did that, you would probably work around most of the errors. Yeah. Yeah. I'm not sure for your second question, which is if new memory order fixes the lack of strongly ordered compare exchange, but the new supported memory orders are essentially all of them: acquire, release, and then sequential. Yeah. Yeah. And thread fences have sequential memory ordering as of macOS 15. But then the atomics themselves, you'll have to wait for macOS 27. Yep. Yep. So I was asked to review a PR on, I think, Reactant to add metal support. It's completely out of my area of expertise, so I'm not sure I can fully help. Oh, yeah. The question was Reactant and metal interoperability and where it lands.
So the PR is there. We can merge it. Basically, it was mainly bytecoded by by Dale Black. The problem with bytecode PRs is that are like these are gigantic, so it takes a while to review, mainly because we are gonna maintain them, and also that LLMs try like to modify things that are not what they should be modifying. The PR is there. It's just that we were busy doing all things, and we want to merge it really soon. We just need to manually edit the things that shouldn't be touching. Yeah, about there are things that should be maybe optimized in the future. We are right now maybe not optimal, but it works and it's tested.
So the question was, are Metal 4's new Metal tensors going to be wrapped or useful for Metal.jl? Um, for the, if they'll be wrapped, it's just a matter of figuring out how and taking the time to do it. It exposed as I think a new C++ library, so it's a lot more work than most of the other things. As for if they'll be useful for Metal.jl, I'm not sure. It feels like it would be just an extra layer of like metal buffer, metal tensor, and then metal array instead of metal buffer to metal tensor. It might make some interoperability with MPS graph easier, but that we'll have to see.
So that's the last talk of our mini. Let's thank all of our speakers again. Let's also thank our AV team who put up with a lot from us. Thank you guys. So we have a 15-minute break. The next keynote starts at quarter to 1800 in the tent. And again, if you have a poster and you're a quick walker, you can go now to set up your poster or do it after the keynote. We have the poster session at 7. There will be food and drinks.